So the title of this talk is Machine Learning for Suits. And I gave a talk like this last year at the same conference. And it was a relatively short talk, about 2 hours, not that short, I suppose. Not a full-fledged workshop. And then over the last year, I ended up teaching the same material to a lot of librarians in Copenhagen and then a whole bunch of Harvard students. A lot of them did not have technical backgrounds. And the sort of realization dawned on me that you really actually don't need a technical background to understand most of this stuff. It's really not that complicated. And lots of books and other things, newspapers and all will do a disservice to you by sort of not actually presenting any math to you whatsoever. And I won't do that. I will actually present you the math. You won't have to actually do it because these days, if you actually even do the stuff using scikit-learn or TensorFlow or any of these libraries, you don't actually have to do the math. They do it for you. But you do have to have an understanding of what's going on. And that understanding is not hard. So it's kind of like, we do this as programmers, right? Something is a black box. And you don't know exactly what's going on, but you have some kind of notion of smacking the black box and saying, okay, these outputs make sense, these outputs don't make sense. We'll put our tests around it, and we'll do something. So it's in the spirit of that, to some degree or the other, that this talk is, that you don't actually need to know exactly what's going on, but if you have a conceptual understanding of what you are trying to do, when that fails, you'll know. And that's actually sort of important, not from the perspective of a person, just from the perspective of a person who's writing programs to do machine learning, but from a person who's, if you like, the immediate consumer of that machine learning. In that sense, you might be an academic in a particular field. You might be you might be a pointy-haired boss. You might be a marketing manager. You might be any of these things. But it's a general kind of literacy which you probably ought to know in terms of sort of being able to consume your data in some fashion or the other. So that's the target audience here. It's not the complete layman. It's a person who has a degree of interest in this for some reason or the other. And so suits is just a sort of like, a overall word to sort of represent different bunches of people. But the point being is that you're not a technical person necessarily. And even if you are, I think this may actually be kind of useful and fun. Okay, so a quick intro to myself. I did astrophysics and astronomy. Specifically, I worked in dark energy, and dark energy is one of these very sort of interesting fields. Way back in the 90s, they were using Bayesian techniques when a lot of other scientific disciplines hadn't caught up to it. And there was a very specific reason for that, which was that A, there was a lot of data, B, there was a lot of experiments, and C, there was no simple way to combine the data from these multiple experiments, because it's not easy to combine data from multiple experiments because all the conditions change. All the things you're holding constant and so on and so forth change between the experiments. And so you have to be very careful about how you model it or you'll get the wrong results. If you say each experiment is just an independent experiment and I'm going to combine the results that way, you'll get everything wrong. So that's why. So that's how I got kind of started into this whole business. And then astronomy itself, over the 2000s, has become a sort of multi-terabyte to multi-petabyte kind of field, where you have these telescopes taking stuff. For example, Kepler and other satellites which are looking for extraterrestrial planets. Extrasolar, I suppose is the right word. Extrasolar planets are basically saying, okay, here's this piece of sky, and I'm going to sample this piece of sky, every 1/20th of a second or something of that sort. And I want to find an object that's moving over here, for example, because it's a planet. Or I want to find an occultation, which is what happens when one planet goes in front of the other, or one planet goes in front of the sun. You get something like this, boom, and so you get light which is going like this, like this, like this, and it drops, and then it goes up again after the planet's moved out of the way. And so you're looking for this sort of thing. But you're trying to do this at 5 hertz or something of that sort, over huge amounts of the sky. So astronomy had to basically go in this direction of trying to figure out what to do with this. So machine learning techniques are very highly used for all sorts of stuff. Some of this for what you might call anomaly detection. A planet would be an anomaly. A planet creating an occultation would be an anomaly. Some of it is for more like, I wouldn't say mundane, but sort of like regular classification tasks as to what kind of star this is. So this is sort of where this is coming in from. And so that's how I got into all of this stuff in the first place. And what I do nowadays is some of that, but I'm also I have this little consultancy called X with a good friend of mine, and who was also a PhD student along with me. And we've been lucky to actually deal with all sorts of interesting problems like maize yields in Iowa and microfinance predictions in India and things like that. I've been working for this course CS109. I don't know if you guys are familiar with it. If you're not, go to cs109.org. All the slides and videos and notebooks from that class are available free online. And it's a good resource for machine learning stuff. And not just machine learning stuff, but data science stuff as well, visualization and all sorts of stuff. It's a fun course. It's a crazy course. My first 2 years back, it started off with about 200 students. Last year, we had an enrollment of about 520. And therefore, we had a staff of about 25 people just to run the course. And that had its own issues as to predicting when people would finish grading their homeworks. This year I'm teaching CS207, which is a sort of computer science for scientists course. It's kind of like the whole inverse thing. It's the course I wish I had when I started out, so that's why I made it. And then there's the AM207, which is a technique on stochastic optimization, which we'll talk a little bit about today, but not much, and Bayesian techniques. So I'm lucky to work on interesting problems, and I hope everybody is lucky from that perspective that we live in interesting times as far as this stuff is concerned. So if you're working on interesting problems, life is fun. Okay, so just to sort of lay out of the land, what are the kinds of problems that we're trying to solve? One class of problems are classification problems, and they're of the type, they're of the yes/no type. Will a customer leave my company? When you go to the ATM and they say, okay, here's a check. Is this a check? Is this a check deposit? Is this a cash deposit? If it's a check deposit, how much is it? Just those kind of questions. Based on some classification, are you a man, are you a woman, are you something else? What will you buy? Less flippantly, you have cancer. And if so, what should we do? Is your email spam? Amongst your friends, whose picture this is? All of these things, which are actually now inside cameras and so on and so forth. All of them have their antecedents in this sort of field. Okay, it's funny actually, but about 10 years back, you did have really poor kind of face recognition and such in cameras. And now you can actually do, this is my wife on the camera right off the bat. You don't even need that much of, once you have sort of like a pre-trained network, which is done outside, you can actually get that stuff into the camera and use it. And there's another class of problems, which are regression problems, which are really predicting numbers, basically. So how many dollars would you spend on something? Are you creditworthy? Are you not creditworthy? And if so, what's your creditworthiness score, for example? How many people vote for Bernie PAs before the election? Questions like that. Used to predict probabilities for classification. And there's an entire other class of things which are actually somewhat even more complex, right? Which are things associated with causal modeling. It's one thing to say that if I go to a supermarket, I buy more beer when I buy more milk. It's another thing to say I buy more beer because I buy more milk, or I buy more milk because I buy more beer. And so that's a much harder problem to solve. And typically it's required experiments to do it, but sometimes you can get natural experiments to try and do this kind of stuff. So we won't go into that at all. And I think that's probably, leaving out deep learning and all that stuff aside, that's going to be one of the more interesting sort of notions of how all of this predictive stuff plays into causal modeling in the near future. As more and more people from those fields, which have typically done causal modeling, like sociology or economics, get into this business. And there are other kinds of learning. There's everything I talked about right now is what's called supervised learning. It's basically you have a teacher, and the teacher tells you that some of these things are of one type. Some of these things are cars, and the other of these things are snails. And you go and learn from the teacher, and then you figure out. There's reinforcement learning, in which you do this kind of online, basically. As you get more and more data, your learning becomes better. And there's unsupervised learning, which is basically you don't know what things are there, and you try and figure out which of these things are different from each other. So all of these are sort of at the intersection of computer science, maths, stats, and common sense. The common sense part is the part where you're actually trying to figure out what features you use. And this is one of the main things a lot of data scientists land up doing, and actually domain experts land up doing as well. Because you can get algorithms to do this. One of the great things about deep learning, and why people are so excited about it, is it actually learns representations that you should use. So if deep learning is trying to figure out faces, it'll actually try and figure out, oh, okay, this is the nose ridge, that's the cheek, and so on and so forth. And it'll use these as features to say, okay, this cheek is different from that cheek, so this person could be different. This nose ridge is different from that nose ridge. Maybe these people are related or not related or something, these kind of things. So you can do it in an automated fashion using this sort of unsupervised learning thing. But if you have sort of like more domain expertise in it, you can actually speed up your algorithm quite a bit. And so your domain expertise, which I'm also calling common sense over here, does not go away, no matter what you do. But the funny story which I read in this book, Bayesian Reasoning and Machine Learning by David Barber. And so the funny thing is that he's trying to teach us what a sports car is. And he cries out sports car and a sports car passes by, and then he asks his son what a sports car is. And the son thinks it's a VW Beetle. Because all sports cars are red, right? So you gotta get your features right. Okay. So this talk is divided into 4 different parts. Part 1 is really the sort of nitty-gritty stuff about the nature of learning. What constitutes learning, what are the various concepts in learning, so on and so forth. In part 2, we'll actually go a little bit more into some of the technology associated with it, and some of the various models that people use. In part 3, we'll talk about neural networks, and deep learning specifically. It has this great mystique around it, and I'm here to tell you it's not actually that mysterious. Deep learning is nothing more than matrix multiplication plus some really good computer programming, plus really, really, really powerful machines, and GPUs, of course. And the 4th part will actually go into evaluating your machine learning algorithms. So this is sort of like the part where, if you like the tire hits the road. You can do all of this stuff, but if it's not giving you good results, then it's kind of useless. And by good results, I mean it depends upon your case, right? I mean, are you preventing people dying from cancer? Are you increasing your profit? Are you, whatever your particular aim in that situation might be. Okay, so the nature of learning. So as I said, there is going to be mathematical formulas here. There's going to be sort of like diagrams illustrating them. So don't get frightened if you see them. They don't bite, and they're actually kind of useful, as you will see as time goes on. So the example I want to start off with is that of a polynomial. And a polynomial is basically a function which takes some input and gives you some output, but does it in terms of, the simplest polynomial is just something which is flat, like this. So that's just one level, so one number. The next polynomial is a line. The line is kind of like that, right? It needs 2 numbers to characterize it. You need to know what the sort of level is, and then you need to know what the slope is for the line. Then you go to the next level and you look for quadratics, and that looks like parabolas, and they have some kind of curve to them. And then you go for the next one that's cubic, and that has some more curve to it. And then you go for the next one. You get my picture. You introduce greater levels of curviness as you go up to higher and higher powers. And you can combine them. And that's the most general thing of a certain degree of curviness, basically. And so the basic idea here that we're getting out of this is that as you increase this power, or the I which you're seeing over there, or the N which you're seeing on the left-hand side, you're increasing the curviness of these functions. And so you can represent things which are more curvy, essentially. So just as an example, if you look at this plot over here, I'm not sure how clear the axis is, but on the left, the value of the top is 10 to the 5, and the bottom is 10 to the minus 3. That's 8 orders of magnitude that I'm spanning. If I randomly choose coefficients for, I think this was maybe a 10th order polynomial, and those coefficients are relatively small, I'll get some nice sort of like well-behaved blue and green line between 1 and minus 1. But if my coefficients of these polynomials are large, right, then I'm multiplying, say, a number over here, like 0.4 by maybe 1,000,000, and I can get something really large. So depending upon the coefficients, I can get all sorts of behavior. And this is kind of important. We'll come to it in a second as to why. And so what we'll do is we'll call all polynomials of a particular kind. So all functions. When I say polynomial, I just think of functions, something that maps something to the other. Of a particular kind, a hypothesis space. So all lines, whether it's like this or like that, we'll call it the hypothesis space H1. And it's called a hypothesis space because you're basically saying that my hypothesis is that this problem can be solved by fitting a straight line to the data. I don't know what that straight line looks like, whether it's like this or like that or any of those things, but it can be solved by that. That's my hypothesis. Maybe a good one, it may be an awful hypothesis. I don't know. There's another hypothesis there which says that I can fit this data by using 20th order polynomials. This is a more complicated hypothesis. This is saying that this data has some kinks to it, has some curves to it, basically, and I need to have something more complicated to fit it. And so I can pick off any number. I use the number basically to index how complicated something is. So H100 is more complicated than H20 is more complicated than H1. That's the notion. Okay, and that's the notion you should get out of this whole hypothesis-based notion. It's trying to figure out how complex something is. We'll come back to this notion of complexity of hypothesis spaces again and again and again, and especially when we talk about neural networks. Yeah.
So, I mean, this is obviously maybe simple math for someone.
Mm-hmm.
Really complex for me to be a math since
Sure. Let me just interrupt you for a second. If you at any point, if you're not understanding something, interrupt and ask. It's important that you get this first part correct because the rest of the stuff will become super easy.
Right.
Yeah, so shoot.
So then, like, if you go back a slide
Mm-hmm.
where you had regression or, you were...
This one?
Essentially, there's a question that you're trying to answer. And behind that question, you're saying, okay, I'm going to formulate a hypothesis.
That's right.
That hypothesis you're trying to convert into an equation.
That's right.
Which is the equation that you put there.
Yep.
Right? And so then, can you take, like, so now let's go back to that.
To the slide?
Yeah.
Yeah.
So now, here, that if it's a straight line, like for a layman's term, right? If it's a straight line and you can say, here is the correlation between the two variables, then my hypothesis is correct in the simplest form, right?
Yep.
Now, when you go and you talking about slopes and curves,
Mm-hmm.
and can you clarify that, like with one real problem?
Yeah, I will. In fact, I will actually do that.
Right.
I will go into actually multiple real problems.
Right.
And show you what these various things are. So at this point, there is no data. At this point, the reason this slide exists is to show you, is to basically get this notion that there are different complexities in these functions.
Right.
And the simplest one is one which is flat like this.
Right.
The next more complex one is the one which is a line.
Right.
The next more complex is a quadratic curve.
Right.
And this notion that you should get is that there is a complexity index for this function, and the index over here is this one. Or this one. This function is more complex than the other.
How do we know, I mean, again, for people who are looking at the applications, right, who are not actually coding.
Mm-hmm. How do you know which one of these to use?
Yeah.
You don't. The answer is you don't. This is the problem. This is the major problem. In fact, in fact, the entire talk is about actually trying to figure out how we might choose a correct complexity for this. So yeah, so just bear with me. It'll come. Okay. So now here is some data. So an example of this. So I generated this data as a sort of like one-dimensional problem here. But the idea behind this data is, for example, this is a, you could say, on the x-axis, it could be, for example, how religious you are. And on the y-axis, could be the likelihood that you vote Republican. Okay, yeah, go ahead.
Do you have the slides available for this? Do you have the slides available?
I will. Yeah, I haven't uploaded it anywhere as yet, but they'll be totally, so you don't need to copy anything. Yeah, they'll be everything will be available. Do not worry. Yeah, so this is, and you can see that this is basically slightly curved. You look at the data points. Don't look at the line fitting it. Look at the data points right now. It's the same data points on both sides. And there are two different hypotheses I use to try and fit the data. What do I mean by fit the data? I'll come to that in a second. But just look at it visually right now. And if you look at it visually, you get the notion that this basically captures the zeitgeist of the data, that it's going up in some fashion or the other. But it actually misses out some of the details. Right? The zeitgeist is correct, it goes up, the more religious you are, the more likely you are to vote Republican. And I haven't said anything about what else you are. And that will become important in a little bit. But suppose this was the case. And so this looks like it's not the best possible thing I could do. So this is not complex enough, this line, to actually capture the data. So I need to find something more complex. So here, on the other hand, I'm using a 20th order polynomial. And you might say, wow, that's not actually that complex a curve. It doesn't need so many wiggles. You didn't need to fit a 20th order polynomial. You probably have a good point. But the notion is that a 20th order polynomial can be found that fits this data really well. And that's the notion you should take out of this. And it seems to look better than this. This gets the zeitgeist, it does not get the details. This gets the zeitgeist and the details. Okay. So, keeping that in mind, this problem is, in its most basic form, it's called the approximation problem, is that I've been given data which was presumably chosen from some function by the Lord, right? And I have, and Lord, of course, being mysterious, doesn't tell me what this function is. Could have told me the function and saved me a lot of work, but didn't, right? So I have got to figure out what this function is, and that's what I'm trying to do. And it's an approximation problem because the function may be completely different. It may not even be a polynomial, right? It may be something completely different. Whatever generated this thing in the real world. It may not even be something representable as a function. I'm trying to fit a square peg into a round hole here. But hey, I've got some technology and I want to use it to figure out this problem. And if it doesn't approximate enough job, I'm happy. It gives me an idea. And that curve seems to do a better job than the one on the left. Okay. So, the previous slide I said look at it visually, but visually what are you doing? So one of the things you're possibly doing, it may not be exactly what your brain is doing. I actually have no clue what my brain or your brain is doing in this particular scenario. But one way you could do it is to just take the distances from a curve or a line or something to the data, the vertical distances, right? And minimize the total vertical distance. Except that would not work particularly well because if you say it's positive on the top and negative on the bottom, those two might cancel each other and give you a distance of 0 and you've done nothing. So you square. So this way you take off the sign. You square the distances, that's what I have over there, yi minus h1 of xi, where I is each data point. And that little symbol below says yi belonging to the data set D. So that symbol, the E-like symbol, it means in. And I'm going to square it, and then I'm going to divide by the number of points I have, because clearly if I have more points, this is going to become bigger. And I don't have a way of comparing two different problems if I don't divide by the number of points I have. So it's the distance from the line. It also goes by various different names. It's called a cost, it's called a risk, it's also called an energy. And there are reasons that it's called all of these things. There are some rather subtle connections to physics, which is why it's kind of called an energy over there. But you'll hear all of these different words: cost, loss, risk, energy. And now you say, okay, the game I am playing is I'm going to minimize this risk. And if I minimize this risk, and I need to minimize it with respect to the parameters in this problem. Remember that when I write a polynomial, basically it has some kind of parameters like theta 0, theta 1, theta 2, theta 3, which are coefficients, numbers in front of the thing, times x squared, and x represents a piece of data, right? So I have to find these parameters to find the actual polynomial. So in a straight line, I have to find the slope and the intercept. That's what I have to do. So I got to find that intercept between 2 and 3 out there at whatever slope that line has. So that's my game. And so what I'm going to do is I'm going to minimize the distance. So I'm going to take all possible lines, find the line which minimizes the distance, read off the slope, read off the intercept, and I'm done. That's the basic game. That's actually the game in machine learning. That's it. We can all go now. There's really nothing more to it. It's all a question of finding different technology to do this. It's not that simple, but that's the basic concept behind it. Okay, so I'm going to minimize square distance from this line.
So, one second.
Yeah.
So, again, this sort of math heap, this will come up probably as, why are you here if you don't know this, but I still have to ask.
No. This, you don't, yeah, you should feel free to ask.
What does the slope represent and what does the
Intercept represent?
Yeah.
So the slope represents how fast things are rising, right? It's basically saying that, for example, in this particular example of religiousness, it's saying that per unit of increased religiousness, as maybe figured out by your answers on some kind of test, how much more likely you are to vote Republican. So it's the marginal change, if you like, as economists would like to put it. That per unit of religiosity, how much more likely you're to vote Republican. So that's basically giving you an idea of that. The intercept's giving you an idea that what's your inherent propensity to vote Republican. You're not religious at all, but you have some inherent propensity to vote Republican here. So it's telling you what that is. So that's the sort of interpretation, and this interpretation varies, right, from one model to the other. And as an analyst, as a business analyst, for example, it's important that you actually try and understand what these things are. And this is one of the criticisms, by the way, of some of these deep neural network models is that, okay, they work. We have no clue what's going on. And in some of them, we can actually figure out what it is, because in convolutional neural networks, when you're looking at images, you can see what the image features are. This is looking at noses, and that's looking at cheeks, and so on and so forth. But in some of these other problems, it's really actually hard to figure out what combination of factors is going in. And so sometimes people don't like such models because it's lost interpretability. But it does happen that you have models which you can't interpret. So you have to kind of get used to that as well. So one of the things to remember that a lot of these cool stuff that's happening, for example, in deep neural nets, it's happened in the last 2 or 3 years. This is a very active research field. And it's a very unusual time in I think, the history of research when stuff that's, papers that come out, basically, in like January of 2016, get productionized in February of 2016. And I think that's also because a lot of the large companies like Google and Facebook and Baidu and all actually slurped up all the big researchers and big research groups. And a lot of the research is coming out of there. And the flip side of that, of course, is also they have lots of the interesting data. And that's why that's what's driving some of this stuff. Yeah?
And neural networks is really old.
Yeah.
Why is it only 2-3 years that?
I'll come to that. Yeah, I'll absolutely come to that. It's an interesting question.
Do you mind repeating what you said, like this is the crux of machine learning?
The crux of machine learning is basically this minimization. So machine learning is an optimization problem. To zeroth order, if you don't take anything away, it's basically you're going to write a cost function and energy function of some kind or the other, and you're going to minimize it. All neural networks do is basically allow you to actually, if you want to know what neural networks do, is that they basically write very complex models, which minimize the energy in some fashion or the other. And it's a new way to solve these complex models, which actually is much more, sort of like, has these different layers on which you can sort of understand you can try and understand what's going on in these various layers. But as you put it, all the technology for neural networks has been around, actually some of it since the 60s. Yeah.
Sorry,
yeah.
Go off of this point. So basically, the intercept for that slope would be, and using your example, if the person was not religious at all, that's how likely they would be
to vote Republican. Yeah, and that will change from model to model. So you have to think about it fresh. Yes.
Can you repeat the questions or have them use the mic?
Okay, I'll do that. Yeah. Okay, so this is what it means to fit, and I'll keep on using this word fit again and again. It's basically minimizing this risk and finding the parameters of the problem. Okay. The specific kind of fitting that we do over here, specific kind of minimization is called in the field. So I will actually use, you can see the jargon out there, and I'm keeping the jargon out there because you'll see it in papers and so on and so forth. You don't have to call it empirical risk minimization, but it's kind of useful if you see it in a paper or in an article, you know what it is. So I am putting it up out there. And so basically the idea is the following. In life, you only get to play with samples. You don't get populations. For example, if you're actually trying to predict an election, you can't go out and ask everybody who they're going to vote for. Well, that would be the election, right? If you're a pollster, you go and ask 1,000 people, and you'll try and figure out from those 1,000 people how this election is going to go. So you only get samples. So you have to understand your model on a sample. So two things need to happen. Firstly, you have to hope that your sample is representative of the population. Many times pollsters get things wrong. For example, a lot of people don't have phones these days at home. I don't. I just have this, right? I'm sure quite a few of you don't have landlines either. You just have a cell phone. And for a while, what pollsters were doing is that, because you couldn't call people's cell phones, they were oversampling the people who had basically home lines. And people who had home lines tended to actually skew older and more conservative. And they were sort of over emphasizing therefore Republican mixtures inside their samples, and that's why they got a lot of things wrong in 2008 when Obama won the election for the first time because everybody was not sampling properly. In 2014, in the last Senate elections, the problem went entirely the opposite direction. Basically, they had far fewer Republicans. So this changes from time to time as polling techniques change. But it tells you that something is particularly important, that whatever sample you chose, it's better be representative of the population. If it's not, you're in trouble. Right? You may be able to constrain your model. For example, if all the people in my sample were very religious, right, I could probably constrain this model very well over here and not tell you much over here at all, because I don't know how less religious people behave. I have no clue. So if I want to predict less religious people, then I'm not going to do a very good job. So in that sense, your sample must be actually representative of your population. So that's first thing. Now on your sample, what you're going to do is you're going to minimize this distance. You're going to minimize this risk. You're going to minimize this cost. That's the game. That's the A over there. You minimize it on that, and you minimize it within your hypothesis space, right? You say, I'm going to minimize it amongst all the straight lines. Or I'm going to minimize it amongst all the 20th order polynomials. Or I'm going to minimize it amongst all the sine curves. Whatever class of functions you choose. You do that, and then B, you hope that the risk on the population is roughly the same as the risk on your sample. Which is just another way of saying you hope that the sample is actually representing the population well. Because if you only got the more religious people, and not the less religious ones over here, then you're going to have this problem that the error on these less religious ones is going to be so large that the second thing is not going to hold. Yeah?
So you said that you first decide on the minimization, right? And then you choose the class of function on which you're going to minimize it. But
No. First you choose the class of functions.
right, then if you don't have your sample ready, how do you choose the class of function in the first place?
So usually you choose the class of functions by kind of looking at whatever sample you have. You need to have a sample.
Okay.
And you say, okay, I do some exploratory visualization of this whole thing. Yeah, this looks roughly, if I did an exploratory visualization of this data out here, this roughly looks linear. It's not a bad choice to choose a straight line to. So I'd say, okay, I'll start with that, and then I'll go more complex from that point onwards.
So it can be an iterative process, right? Like you might have to change your function and then change the class.
Absolutely.
Right? Okay.
And there's another way of thinking about this, which we'll come to, which involves the word regularization, which is you actually start with more complex stuff first, and then try and actually, basically constrain its complexity. So there are different ways in which you go about this process. Okay, so that's the whole idea of empirical risk minimization. 2 points. Minimize on your sample, this distance or risk or error or whatever you want to call it, and then hope and pray that it's actually representative of the population, because you may have got that wrong. Yes?
What does the D stand for?
The D stands for data. I always use the script D to stand for to mean my particular data set, my particular sample over here. Okay, how do you do these minimizations?
You have a question back there.
Yes.
Yeah.
there an approach that you define to choose that sample?
So the question is there an approach that you might use to choose samples? The answer is that's one of the most complicated things in the history of humankind. There have been like tons and tons and tons of work done by sociologists, political scientists, and all kinds of stuff. Let's just talk about elections for a second to try and figure out how to sample it, and they still get it wrong. So every cycle, there are about 5 or 6 different pollsters, and you'll see this happening this year. And one of the pollsters gets something wrong because their sampling method was wrong. They kind of keep these sampling methods proprietary to how they do their polling stuff. So what Nate Silver will do is he basically will average all of the different pollsters and put in different weights on how well they do in certain scenarios. So he does a weighted average to figure out what you should actually use. So that may be one way to do it if you don't know what the quality of your samples is. But you bring up an incredibly important point that the quality of your samples needs to be high. Now this is relatively simple when you're sampling from your business data, because hopefully you have good processes to measure stuff. It's relatively hard when you're looking at people, when you're trying to predict something to do with people, because then your data is kind of poor in general. So yeah, it's not an easy problem. So in regression, actually, specifically in linear regression, you don't have to do anything numerical. Everything actually works out in algebra. You don't have to worry about it. But in general, whenever you minimize one of these things, you do a process that looks something like this over here. And the specific minimization I'm going to talk about is something called convex minimization, which is what you get when you choose to take these squared distances and add them, because this is a parabola. So basically, an x squared type function looks like a parabola. It looks like a dish. And one of the great things about dishes is that there's what's called a global minimum. There is a point at the bottom of the dish. A dish does not sprout lumps and all kinds of things all over the place, so that if I rolled a marble, it would go into one of those lumps and not go to the bottom of the dish. If I put a marble in this dish, it's going to go to the bottom. And that's actually the game you play. So think of that red thing as a marble over there. And basically you let the marble roll. And the marble is going to roll in the direction of the highest steepness. This is kind of intuitive, right? You put a marble there, it's not going to go off like that and go, it's going to go boom, all the way down. In fact, it's going to overshoot, and you see that's what happens there. And then it's going to come to a stop, and then it's going to go back, and back, and back. And so basically, it'll get to the bottom. Now this is assuming, of course, you have a dish where you have complete symmetry and everything else. That's not necessarily true, right? It might be lumpy in some kind of fashion, but as long as it doesn't have a local minimum, right, we're in good shape. You're going to get to the bottom. So this is a notion of convex minimization, and this method is called gradient descent. It's called gradient descent because the gradient is that blue line you see over there. That's basically the slope. It's basically telling you what's the tangent at that point. If just one second, it's 1 dimension it's a tangent. If it's 2 dimensions it's a tangent plane. It's basically telling you what the direction to go in at that point. Yeah, shoot.
Convex minimization is something that you use when you are
So polynomial, it doesn't have to do with the polynomial functions per se. It has to do with this distance I chose. I chose this to be a square distance. There is no reason that this is an a priori better choice than any other. For example, what I could have done to get over this problem of pluses and minuses is I could have chosen to take the absolute values. So I would take the distance. If it's negative, I'll make it positive. And then I'll add all of those. That's a much more complex function to try and minimize. So the convexity comes from this particular choice of distance function. It's a kind of natural distance function. It happens to be nice. It's convex and makes things really easy. So one of the crazy things about neural networks, and that's why people didn't do them for many, many years, and this goes back to your question, is that when you do this kind of minimization in neural networks, it's not convex. You have many of these local minima. So the local bump downs and it goes up again, bump downs and goes up again. And back in the day, in the 80s, when they started doing this, computers were not powerful. So many times you do the stuff, you get stuck in a local minima. And the moment you get stuck in a local minima, you got to give the damn thing a kick. So then it goes out of there and it goes to the next local minima. There can be millions of local minima in neural networks. Depends upon how many neurons you have. And so, because you have to keep giving it this kick, it takes a lot of computation to do this. And we didn't have it back in the 80s. In fact, Google has actually put out a product which I think it uses internally, but it's available outside. At least the paper is available, so people have cloned it, which is basically a database server which actually does gradient descent. It takes out these different portions of your, it uses what's called stochastic gradient descent, which actually doesn't take all your data, it takes just parts of your data to do things with. And basically Google splits up a part of your data on multiple machines, and it actually solves them in parallel. That's the whole game. Because it's just so important for neural network stuff and so on and so forth to do that. But this sort of stuff you couldn't do in the 80s. You just didn't have the technology. So you had very, very small neural networks, which you solved. And so nothing to come, basically. Yes?
So you're trying to minimize the distance, you're trying to cost or risk, essentially, you're trying to minimize that part we thought, or at least what happens, why, like what does, with large data sets or whatever, what does that do, and then how did we go from here to then the gradient descent?
So the gradient descent is just a mechanism to do this minimization. So the point is that if you look at this, right, and if you look at this in a space which has W0 and W1 as its coordinate axes, so that's the space that this thing is showing you here. I've called it theta 1, and it's called theta 1 and theta 2 in the place where I picked up this image from. But imagine that was one of these axes over there on the bottom. The theta 1 is slope, and the other one is intercept. So this is the space of all possible slopes and all possible intercepts, i.e. the space of all possible straight lines. This is what that distance looks like in that space. So this is after taking all your data points, all the x's and y's into account. This basically is just quadratic in terms of the slope and intercept. And I have to find the minimum of it. So I use gradient descent to find the minimum of it. And gradient descent is basically start a model, get it to roll, find out where it goes. If it's convex, which means it has just one of these bowl-shaped things, it has no like sub-bowl and super bowl, that thing, it's going to go to the bottom, and you're done, basically. And so that's the way you do this minimization. And as I said, for the polynomial problem, you can actually solve this exactly. You don't even have to do this minimization. But for other problems, you do have to do the minimization. Yes?
So I know that you're trying to use gradient descent to find local minimum, but why do you need to find local minimum?
No, you find in convex things, you're finding the global minimum.
Okay.
Yeah. Why do you need to find the minimum? Because you want to minimize the distance. Otherwise, you've not got a good fit, right? Otherwise, I'll say, here's the data which goes like that. That's a good fit. That's our minimum distance, basically. Yeah.
So I know that you're explaining us all of this, like, that these are different methodologies to, like, minimize and come to the local minimum or whatever. But, like, can you just give an example that if I'm trying to, or are you going to do it later, that, like, I'm trying to solve a business problem, and then, like, this is the methodology that I'm going to use, or let's say I come up with a function, like, y is equal to mx plus c, and then, like, what am I going to use to actually, like, and what am I minimizing? Like, just from a business perspective.
So you're minimizing m and c. You're minimizing to find m and c.
Right.
So you're minimizing this distance. Now, what does this mean from a business perspective? It could mean one of many different things.
Right.
From a business perspective. You may be trying to predict what your sales are next quarter. That's your y. Your x may be, what's the performance of your, let's say, Bangkok office. And so now you're trying to minimize your sales next quarter based on the performance of whatever performance means over there, right? So what you're trying to do is you're trying to find the appropriate function to sort of capture the zeitgeist of how the sales vary with performance. And so once you figure out what these coefficients are, you'll actually write out the equation. Y is equal to intercept plus slope times sales, right? Sales is equal to intercept plus slope times performance. And you'll say, okay, now if the performance, I increase the performance by this much, by 1 unit, how much can I increase my sales? That's the prediction problem. Ultimately, you're interested in finding Y for new X. Like if I fired 5 people and my performance decreased or my performance increased, what would happen? So that's the business. That's the business end of it.
Right. So I know this is like math, but is there like a practical application that will help us like do this minimization, or do we have to do math to do it? Like, do we have to actually write the equations, or are there like packages, or are you going to tell us?
There are. I won't actually talk about any specific packages,
okay.
But you can just go out and look at the exhibitors out there. There's one after the other of them, which there's RapidMiner, there's all kinds of people, and there's scikit-learn in Python. There's Carrot and R. I think Max Kuhn is here. He's going to be giving a talk on Carrot. So there's all kinds of stuff. There's a talk on scikit-learn after this in the afternoon. So if you actually are interested in doing the nitty-gritty math stuff, that's actually an absolutely fabulous workshop to go to. And it's in Python, but you need to know some Python for that.
So ultimately, like the problems that you put earlier right now, what we trying to understand it, right? And there are recommendations engines out there, and we're trying to say, okay, for search, people who do this, what are they most likely to click on and buy and do that. So where does this minimization? So how do I take all that data? Ultimately, machines have to do it so that we don't.
Yeah. So to put it to you this way, each one of those products has a minimization routine in it.
Okay.
It's doing it for you. So what you should, actually sort of understand when you buy a product like this is to understand what exactly it's doing. Because there are some of these situations where these minimizations are very good, like doing the square distance is a very good thing. In some situations where it's not, it's actually an awful thing to do. So different techniques actually matter. There are these theorems in machine learning called the no free lunch theorems. They're basically saying that no machine learning method is actually terribly better than any other machine learning method. You have to get your representation in which your data is correct. If you don't, you might actually underperform. And so this is the question as a manager. This is the question you need to keep asking. Are you actually squeezing? Are you using the right representation? Are you using the right kind of algorithm, so on and so forth? What you would do to actually do a recommendation engine is actually fairly different than you might do for something else. But we'll come to that in a little bit later. Okay, so convex minimization. I'm actually going to skip over this slide. This is basically giving you some idea of the kind of schematic of how things go. It's not particularly important. Here's the notion here. That graph I showed you earlier, right? The points on a vertical scale are actually quite close to each other. They're changing, but from one to the other, they are actually quite close. Now look at this over here. These points are all over the place, even from one point to the next. And the reason for this is noise. And what is noise? I'm trying to figure out how you vote based on your religiousness. That seems like a terribly stupid idea, right? That's not the only reason you vote Republican or you vote Democrat or something of that sort. Your own various different access to grind. Maybe it could be your race. It could be how some government functionary treated you badly, so you might not want to vote for someone from that party or something of that sort. There are lots of various things that go into your decision, basically. As a pollster, if I only ask you about religion, I have very incomplete information. So because of this incomplete information, I might have two people who are almost identical in all respects, but they vote in very different fashions. Or for example, in a more business-oriented example, if I have two people, seem to have like the same amount of income, the same kind of family structure, and all of these sort of things. One of them basically goes bankrupt, and the other one doesn't. Goes under on their mortgage, and the other one doesn't. So what on earth's going on? Or maybe you didn't know that one of these people had a divorce or something of that, all of that sort. So you had incomplete information. So that shows up as noise, and that shows up in schematically speaking in things like this point being so down here and that point being so up over there. And so when you have this noise, basically you have this lot of this jiggling of your data. And when you have jiggling of the data, now, which fits better, in your opinion? The line fits better, right? Because what this is doing is that if you look at this 20th order polynomial, because you've started jiggling it, it's got all these points here, and it's going up and down. So what's happened here is that because it's got this additional freedom to curve all over the place, because it's a 20th order polynomial, it's a much more complex function. It says, this data looks complex enough to me, so I'm actually going to see what I can do to fit it, and it fits it with this very, very curvy, complex kind of thing. Meanwhile, at this point, the line over here says, I'm actually not that expressive. I just have a slope and an intercept. I can just do this. And yeah, I'm not going to get the details correct. But the details have got messed up themselves because of this noise. The details are lost in the noise. Because the details are lost in this noise, let me just be safe and capture the zeitgeist. And so the left curve does much better. And the right curve is getting totally sidetracked by the fact that this thing was up here, and this thing was sort of down here, this thing went up there and down. It's getting totally sidetracked. So what's happened is that with this more complex function, you've actually lost predictability. Because if you now ask the question, what's the value over here at this x? It's going to say, hey, it's down here. And you're like, really? That data does not seem to indicate that there's something over here. You did a terrible job on predicting it. You lost your job if you predicted this, basically. So therein lies the fundamental issue that you have to try and figure out in machine learning. How complex should your hypothesis be? If your hypothesis is not complex enough, if I try and fit just a mean to this, I lost my job. If my hypothesis is too complex and I predicted that at this value, yeah, you're going to work around me. You got fired as a pollster, right? So the whole game is hitting the right complexity. Yes?
Right, so like, I'm sorry I'm asking a lot.
There's actually a question.
Okay, so I'll let you go first. Alright.
Yeah, when you're predicting those kind of things, don't you assume that everything fits well, but that could be one of the outlier which is not in the realm of my.
Yeah, totally could be. But I don't have that outlier in the data. Do you see an outlier in the data that far down? No, right? The outlier is only in the function I'm using to try and predict it. You're right that if there's an outlier out there, I have two choices. I can say that outlier is important and try and do something with it. Or I can say that outlier is not important and throw it away. Again, those are modeling, not modeling, but those are choices you need to make when you clean data. That's a whole different thing. We won't actually get into that. We're going to assume that somebody cleaned the data and gave it to us for the purposes of this talk. But you can see that that's the noise that's there. And if I do something that's too complicated, I get messed up. And I'll show this to you in another fashion very, very soon. So just bear with me here. So I'll actually skip over this right now. Deterministic noise. As well. Okay, so here's the kind of problem with this whole thing. You've got this kind of noisy data, right? And you're trying to fit something to it. This data is noisy for multiple reasons. You have incomplete information. You don't know as much about the world. I should actually put this slide back on. There's measurement error. You didn't go out and measure a lot of people. The instruments you used to measure were not good enough. Your samples were small. In tongue-in-cheek, I put quantum mechanics just because things become very unpredictable in quantum mechanics per se, without having any of the other issues. We have a way of dealing with this. It's called statistics, and the two branches of statistics, frequentist statistics and Bayesian statistics. Well, I'll link up my frequentist right now today. And Alan Downey, I think, has a workshop at some point in this conference. He's super good. He's got one on Bayesian techniques. The fundamental weirdness of frequentist statistics, statistics in general, is the following. In life, you've got only one sample. But you are going to sort of pretend you have access to many, many samples. And all the distributions you come up with in statistics are distributions, basically, which would say what happens in these different samples. Here's a number I calculated in these different samples. I said, let's calculate the mean of your sample, right? If I got another sample, I can calculate another mean. If I got a third sample, I'll calculate a third mean. If I get a fourth sample, I can calculate a fourth mean. If I put all these means together, they'll also have a distribution. This distribution is actually the Gaussian distribution. This is the famous central limit theorem that some of you might have heard of. That if you take all these different means from different samples, they look like, the distribution of these means looks like a Gaussian. But the fundamental point is not that over here. The fundamental point out here is that you only have one sample. And from this one sample, you're going to try and make these predictions of things. It's a little bit of a hard problem. You can get the mean from that sample, but to actually give you some idea what the uncertainty in the calculation of that mean is, you need to pretend you have all the samples. And in fact, there's a way to pretend that you have multiple samples. It's called the bootstrap. And the idea behind the bootstrap is basically this. You take any of these samples, okay? And with these samples, what you do is you start sampling from the sample. So suppose I had 100 things in the sample, right? I'll say, okay, I'm going to take 70 out of them. I'll randomly choose 70. Furthermore, I will randomly choose 70 with replacement. What that means is, If I have 100 things, once I pick the first thing, I don't throw it out and have 99 left. I put it right back into the urn. And I have those 100 things. And I again sample. So it's possible I might get the same thing again and again. And that's okay. And so this way, what I basically do is I create synthetic data, and now I can calculate the mean on all these data and get an idea of what the spread of the mean is. And that's kind of important, because if you're going to say that, for example, that my algorithm is better than yours, or my polling model is better than your polling model, or Hillary is going to beat Trump in a particular poll, and if you say that Hillary is going to get 51 and Trump's going to get 49, but the margin of error is 6%, you've said nothing, right? Because those overlap. So you don't want those to overlap, and that's why you need to actually calculate these things. But the reason I bring this up is actually something even more fundamental. Here's a game I actually played. Okay, I actually generated 100 data points. Okay, for this model. From these 100 data points, I picked 30 at random. Okay, on the left side, what I did is I fit a straight line to those 30 points. Okay, it's a nice straight line. But because I chose many such samples of 30 data points, I basically fit many straight lines. And I plotted all the straight lines for you. And you can see that because I have very restricted freedom in this line, right? I mean, it has two parameters. No matter what data I got, most of it actually stayed in all these lines stayed in a very, very small band of lines, which means that the intercept and the slope are relatively stable. Here's where I did the same thing for the 20th order polynomials, and you can see what happened. I got all this hair all over the place. I had some more data over here, so my polynomials were kind of better constrained. Here, over there, I had less data at the edges. The polynomials went all over the place because I chose 30 points at random over here and tried to do this thing. And so it went all over the place. So this is what's called variance or overfitting. You might have heard this word, being bandied about. This is the notion of overfitting, that you basically have a hypothesis that's too complex. And one way to see that a hypothesis is too complex is that if you subsample, or if you take another sample, or if you somehow or the other you have the population, because I constructed the problem like this and I had the population, I take another 30 points from that population, I do the fits on it, I get a completely different fit. Which means I'm completely hosed, I can't predict, right? If I get a completely different fit by choosing a different sample. That goes against what we said earlier, that whatever's happening on your sample, hopefully that's representative of the population. Basically. It's not true for this model, right? It's true for this model on the left. So this is one way of looking at this problem. That if you have too complicated a model, it will basically not capture, it will basically not have any predictability whatsoever, and you'll see all this hair. So that's called variance. On the other hand, if you have too simple a model, look at all of those straight lines I picked, they don't capture the fact that that thick red line actually has a little bit of a curve. So if I was to try and make a prediction between 30% religious and 40% religious, I would systematically overpredict based on these lines. That's a problem too. That means I'm not expressive enough. So that's the problem of what's called bias. I'm biased in the sense that no matter what I do, I'm not going to improve this. So that's the issue that's going on there. And again, so this goes back to what I was talking about earlier, that basically what you want to do is there is this point that you want to balance things at. Is this less complex? Is this too complex? That's the sort of like balancing act that you're trying to do.
Could you please, if you don't mind, explain why the graph on the right, why the different models are not, similar? I didn't get the hair part you were saying, that it has
sure.
Hairs,
So let's just sort of look at this from the perspective of. Actually, let me show you another diagram which will make this very clear. So here's actually a really, really simple diagram, the example of this, which might make this a little bit clearer. So what I'm doing over here, and I'm doing this slightly different in terms of the data size. On the left graph, I chose 5 points. On the right graph, I chose only 2 points. And then I fit a line through those 5 points on the left side, and I fit a line through those 2 points. Well, fitting a line through 2 points is kind of stupid. You just draw it through the 2 points. Okay. But you see what happens. If you look at this, the function that God gave me out here is the sine curve. Okay? Now, if I pick 2 points of the sine curve, I could randomly pick one over here and one all the way down there. In which case, if I drew a line between them, it would look kind of flat. I could have something over here and something at the top, in which case it would be quite high. On the other hand, if I had 5 points, I would be forced to actually get some points along that spine over there, on the left side. Because I have more points there and I'm forced to have something along the spine, you can see that on the left side, all the lines, basically, all the hair, if you like, is in just one direction. It's in this kind of climbing direction of the sign, slightly, brought down because of the right side of it going to the bottom. On the left side, it's all over the place because I have only 2 points. And that's a version of what's going on over here. So what's going on over here is that basically I have few points. I'm fitting a really complex polynomial. So it does that, right? That's literally what it does. It goes all over the place and skips and hops and skips and does all of these things. Okay, now I choose another 30 points. I don't give it the same 30 points. Just turned out that those 30 points, let's say in this region, the point was here. So it did this. In the next 30 points, I didn't get that point, just by my sampling. I got the point next to it, which turned out to be here. So this function goes up instead. So what happens is that's the reason I get this hair. At some point it's going down, this one, and because this thing is saying, oh, I've got to fit all this noise, I've got to fit all this noise, I've got to fit all these points. It goes down in the first case, it goes up in the second case. Whereas what it should have been doing is saying, this is noise. Guys, let's not fit the noise. Let's do something smooth. That's what happens when you choose something terribly complex. It starts fitting the noise. It does not actually fit the data. So that's the critical. This is a good question. Okay, so if you're having problems in machine learning, the answer is almost always overfitting. Without knowing anything, just say it's overfitting. There's a 90% chance you're probably right in that particular scenario. And what these graphs actually show is that actually the amount of data you have does matter. So, as I was saying, I only have 2 points over there. And I have 5 points over there. If I have 5 points, I will do a much better job getting the zeitgeist than I will with 2. That's kind of, you might say that's kind of obvious. But there's a corollary here which is a little less obvious. That if you have less data, no matter how complicated a function is, you better fit a simpler function, because otherwise you will do that, right? If I gave you, so to make it, to sort of put this in an extreme situation, suppose I gave you 5 points, and I said fit a straight line through 5 points. You said, okay, good, I fit a straight line through these 5 points. Then I said fit a 5th order polynomial through these 5 points. What's going to happen? You're going to be super overfit, right? Because it's going to actually pass through each and every one of those 5 points. It's going to interpolate those 5 points. So anytime you flip a point a little bit, so suppose my data was actually now 6 points, and I said fit 5 points, it's going to get completely sensitive to how those 5 points jiggle around, my choice. And so that's the problem, that if you actually have less data, you must fit a simpler model. And so the corollary is not as straightforward to think of as the notion that, yeah, you know what, you got less data, straight out simple. Okay. So, how do we do this? What is the process of learning? Yes?
So, in the case of overfitting, so it has a complex function. So, when you add the data, so is that the solution when you add the data and then kinds of average out?
So, if you have lots more data, yes, it'll, if you're so lucky that you can add more data on and on over time, you can use a more complex function. On the other hand, if you don't have much data to start with, don't use a complex function. You might find later that you use this complex function, and it turned out to be perfectly fine, but you don't know that right at the beginning. Or you use something which is actually probably a better way to do this, which is to use something called regularization. And the idea behind regularization is I am going to choose this maniacally crazy 20th order polynomial, but I'm going to constrain it in some fashion. So if it actually turned out it was a 20th order polynomial, then you can remove the constraint. And that's kind of cheaper, if you like, from a computational perspective.
I want to just frame this question a little bit different. So how do you address overfitting and how do you address underfitting?
I'll come to that. Okay. Yeah. So, we should take a break in about 5 minutes. Let me go through this business of how we actually do this learning process. So what is the process we do to do this learning? So you came to me with a piece of data, right? And I said, okay, I'm going to fit all of this data. And you're like, no, that's not such a good idea because you fit a function to all of this data. How do you know this function was any good? That's the question I'm trying to answer. How do you know that we did any good? So what you must do in that particular case is you hold out some data. That's that pinkish thing out there. It's called a test set. I basically take that data out and I don't touch it. In fact, if you're a boss, you should actually not even give it to your analyst. Just keep it out. Because there are very subtle ways in which you can cheat without even knowing it. So actually even take that data out. So now you get this training set. And what I've done over here is I've basically schematically shown this data set as made up of 5 parts. 4 parts of which are what I'm going to call this training set. That's my sample. This is actually a bigger sample. This is not the population. But I'm making my sample even smaller. Okay? So I have these 4 things and I'm going to train on this. So that's what you can see I've done over here. The blue points in the curve are my training points and the green are my test points. So I'm going to fit basically a model, a hypothesis, to my training set and see if it does well on the test set or not. And so what I'm now trying to do is I'm now trying to get to this notion, to what you were talking about, which is to quantify this overfitting or underfitting and actually detect which one of these is happening. And the way I'm going to detect whether this is happening is I'm going to detect it on the test set. You might say, why? Well, take that extreme example I gave you, right? Suppose I had a data set of 5 points and I fit a 5th order polynomial. What's my error on this? It's 0, right? That's the point. It went all the way through. 0. Now you give me a 6th point. I'm going to completely flunk on that 6th point because it's doing all that stuff to fit those 5 points. And now my test set error is large. So whenever you get into the situation where your training set error is like close to 0 and your test set error is large, you've landed up in the situation where you're overfitting. Because anybody can do well on a training set, right? Basically, I can just memorize it. And I'm going to do well. So that's what this diagram is showing. That if you have a complexity, here the complexity is the order of the polynomial. As you increase this complexity, the training set error is going to look like this. Basically, it's going to go down and down and down. Because I can basically interpolate my data. I can basically pass through all the points and get the error to 0. There's none of those distances left anymore to do. But then when I have the test set error, my test set error will basically bottom out at some point. And then it will start climbing up again because I start doing a really bad job because I'm jumping all over the place. So that place where it's at the bottom is the place where it's just the right amount of jumpiness. So in that sense of those curves we were showing earlier, it's the thing which the straight line that we were seeing is somewhere on the left over there. Maybe over here. Because it did not capture the fact that this thing was curvy, there's intrinsically always going to be some error. You can't get rid of it. That's why you're out there. On the other side of it, basically what's happening is I'm saying this is too wiggly, so the next thing that comes in, my error goes up. So there is some, you can just think about it from this side. It's got to be constrained from both sides. There's going to be some optimal point. And the game is to find this optimal point. And this is true of all machine learning algorithms, whether it's your neural nets, whether it's your naive Bayes, whether it's your support vector machines, this is the game. You want to find that optimal complexity thing to do. Okay, so here is an example. What you see over here is that this is the training set. This is the same example we had there. This is the order of the polynomial. The training error keeps going on as you go around to 28 order polynomials. You're fitting 30 points of data. Your training error goes towards 0. Your test set error starts there. That's when you do the straight line. Complex but not complex enough. Boom, 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 boom. Goes down. And then goes up again. And so over here it seems that this thing is happening at a value of 4. A 4th order polynomial is good to capture the zeitgeist. Now, what's wrong with this picture? Who's going to tell me what's wrong with this picture?
The local names.
Pardon me?
The local names are in
There's no local minimum here. This is a convex problem.
You should use cross-validation.
Yeah, so you're driving at the point that you should use cross-validation. But the point is this, that when I split this data set up, like this, and left one test set out.
If it's not like representing the same set, maybe?
Yeah, so if it's pathological in some fashion. It's like if I have, it is possible to get 10 flips of the coin heads. If you just do 10 flips of a coin. If you do 100 flips of a coin and you got like 10 sets of 10 heads, then you say, okay, something bizarre is going on. This may be a fake, not a fair coin. But if I just got 10 sets, if I just flipped a coin 10 times and I got 10 heads, I can't say that this is not a fair coin. I only flipped it 10 times. And so that could be what's happening there. So what you want to do is you basically want to sort of randomize this or take different splits. So maybe what you would do is you take that fifth one, put it in your data set and take the third one out and predict on that. And when you do that, what you'll find basically is that this minimum point over here will shift around a bit. And so you need to know what that range is that it is. So if somebody quotes, oh, the minimum is at 4 and says, okay, I'm done. Bad. Always ask people to give you a range. Because that gives you an idea of what this algorithm is doing, basically. I'll skip this one. But that's the process that I'm talking about over here. Is that this is kind of somewhat of a sad process, actually. It's a sad realization. Because what you do is you actually eat up even more of your data to do this. So if you're in a low data situation, this is kind of sad. If you're in a high data situation, no problem. So I have these 5 partitions of my data set. I still keep the one test set up. Because I need to figure out the algorithm, what the correct algorithm is based on that test set. What I do is from the remaining 4 partitions, I take out one more. And that's what's called my validation set. And the reason to do that is because I want to figure out this complexity as well while I'm doing this. And if you think about it, something weird has happened over here. Let's say I was fitting the straight line, right? When I fit the straight line, I've actually given you 3 parameters, not 2. I've given you the slope, I've given you the intercept, and I've given you a number which represents the complexity. In this case, the number is 1, because that's the highest power. It's A0 plus A1 times X, right? But what I'm trying to do in this entire process is to find this bottom over here. So I'm actually trying to find D as well. So I'm actually fitting one more parameter. And this is why you need to have this validation set as well. Because there is actually a second fit going on in this game. So here's what happens. This is the game I play. In H0, which is just the flat lines, H1, which is the straight lines, H2, which is the curves, so on and so forth. In each one of these, I take these 4. I train on this, and I compute the error on that. Remember, if I compute the error on this, it's going to be nefariously low, right? It's not going to give you a good estimation. So I compute the error on this. Okay? I write that error down. I'm calling it R out G minus 0 over there. Then I do the same thing in each one of these various hypothesis spaces. Okay? Once I do that, what I can do is I can pick the hypothesis space with the lowest one of these errors. And then what I do is I just train that hypothesis space on the entire set. So this is the process of validation. We haven't gone to cross validation yet. I'll come to that in a second. But this is the process of validation. And the idea behind the process of validation is that I'm going to train on this validation set. I'm going to train on these 3 things. I'm going to find the errors on this and find the lowest error on the validation set. And find that lowest error on that validation set actually allows me to quote-unquote fit for that complexity D, for the order of the polynomial D. And so this is giving me the order of the polynomial. By the way, this should give you some rough notion of what's kind of happening in this process. That every time I try and fit an additional parameter, I kind of need a little bit more of a data budget to do this, if you think about it like that. And so that's the game that's being played. You have enough data in this budget, basically. That's why if you have very less data, fit a simple model, because you don't have enough of a budget to do that.
So Rahul, one quick question, when you do the validation set, right, do you have to make sure that, let's say the mean of the validation set is the same as the mean of the training set or similar, just to make sure that
so you want to make sure that the validation set actually is statistically similar. So there are different ways in which in which you can do this. For example, if you're doing a classification problem, you try and make sure that the rough population and the rough split in the validation set is the same as it's in the training set. So that it's a similar set. Okay. So that's validation, and now you generalize this notion of validation because of the possibility that your validation set was pathological to this notion of cross-validation, where what you're doing in this whole cross-validation business is you're like, okay, I've got these 4. Not only am I just going to do it on that particular set, I'm going to take these 4 partitions and train the model 4 times over here. First time I'm going to use the last partition as the validation set, and this one I'm using the second, this one I'm using the third, this one I'm using the fourth. Each one of these is going to give me a slightly different error, right? What I'm going to do is I'm going to average these errors. And then I'm going to play the same game. I'll look at this in H0, in H1, H2, H3, H4, find the one which minimizes the average error. Clearly, of course, there's also going to be a standard deviation of the average error, which you should actually report when you're looking at this kind of program. Most people don't, and I don't understand why. You'll see in the next diagram why it's actually kind of important to do it. So what you do is you find the appropriate complexity with the lowest cross-validation error, which is this average, basically. And then you retrain using that, so say it was d is equal to 5, fifth order polynomials. Then you retrain on the entire data set, and then you have a test error from that. And if your test error is small, then you've done a good job. Okay? So, skip this one. So this is the graph I was talking about, and actually this is kind of bad because you can't quite see why these things. So it's completely invisible, but there's actually a error bar. This is supposed to be like a green thing going all the way down to the blue line goes roughly around here. Showing that as you get to higher complexities, because of this whole bouncy thing with the polynomials, your errors are very different as well. But then all said and done, basically this thing comes down to like at about 3. So it moves. And this entire thing is roughly flat over here. You can see that all the way from about 1 to 5, or maybe even 6, you do a reasonable job of fitting the data set. 1 may be not expressive enough. In some cases it may be, in some cases it may not be, but it does a reasonable job over there. And then after that it just increases. So in this case your answer to this problem is like, what should I use? Should be anything between 1 and 5, or anything between 1 and 6. It's reasonable. It's not terribly good. This data was probably coming from some other function, but having said that, I'm going to use polynomials to fit it. This is what I can do with it. Okay, so cross-validation is kind of useful because it's robust. If your validation set was just bizarre for whatever reason, something weird happened with it. It allows for larger training sets as well, right? Because now you have these 3 in 1 and 3 in 1, and you're mixing it all up. And the great thing is that it allows for error estimates, and I wish actually that this would translate, but maybe I should just hold this. Nah, I won't hold this up. So here I think it's at d is equal to 3. 0, 1, 2, 3, where you find the minimum.
Excuse me.
Yeah.
You simply referring to error of both. When we're actually doing the actual experiment, we how much statistics?
What do you mean by what statistics?
I mean, how much statistics are we using here? For example, you want to see how close it is.
All right, so I mean, at the very least, you should be plotting the means and the standard deviations. Because if you don't plot the standard deviation, then you say, oh, the minimum is at 3, but if the error bar is that much, and the minimum at 2 and 4 within this error bar range, you can't really distinguish 2, 3, and 4 over here. That's the point I was trying to make, is that basically it needs to be outside of that error bar range to be able to distinguish it as being any good. And that's kind of an important point, that you might, as an analyst, you might go back to your boss and report, okay, I've got a d is equal to 3, let's use that model, and as a boss, you should tell them, really? Show me your error bar, right? Show me what the errors are on this from different sets. So that's the point I was trying to make with respect to this. I mean, if you want to do this really very accurately, you could actually say, now I'm using H, I'm reusing the word H again. Hypothesis, the null hypothesis is that it's at a complexity of d is equal to 2. The alternate hypothesis is that it's at d equal to 3. Are these statistically significant differences? That's what you do. You do significance testing to figure out if these were statistically significant differences. But what I'm trying to say is that you don't need to do that. You can be actually fairly loose and loosey-goosey with your statistics as long as you use your common sense. Anything within error bars, this is the same, basically. That's common sense. That's all a significance testing is showing you. I'd rather you plot it and say, basically. Yes? What is the? That's the error. That's the mean squared error. Yeah. Over here. And the x-axis is the complexity or the degree of the polynomial, and the y-axis is the error. So I wish you could see this, but the error bars go all the way down to here, which is not surprising, given that at higher polynomial orders, basically, you might as well have flipped a coin. Yeah.
So say from 2 to 6 are all within the like a 1 standard deviation, and they're the minimum. And in practice, do you tend to pick the less complicated model, or tend to pick the minimum within that range?
I tend to pick the in between. Basically, it really depends on what you're trying to do. So here, for example, you could pick 1, since this is almost flat. But I do know, just visually looking at the thing, that 1 seems to do not such a good job of getting any curves. So I'm going to choose something which is slightly more curvy because it may do a slightly better job. So, but that's a judgment call.
Okay.
There's no scientific reason to pick to not have picked 1, right? It's just my kind of judgment call.
One last question. In the previous slide, if we can go back.
Yeah.
Sorry.
No, not this one.
Cross-validation. Yeah, perfect. Can there be a scenario where the errors themselves in each, let's say H0, will actually vary a lot?
Between each of the folds?
Yeah.
It does happen. In fact, that's what's happening over here. That the reason that you see this cut off is because there is actually an error bar going all the way over here. So between cross-validation folds, the error is just varying so much. And then the reason it's varying so much is because you're terribly overfit. Because you're fitting so much to those specific points in those 3 training folds. And then you're testing on those specific points in the 4th fold, that you got a certain error the first time, and the next time you got a completely different error. Because you divide a completely different polynomial, 20th order polynomial. Completely different, it has nothing in common with the other one. Whereas over here, you have something in common with the other one. So this is basically a feature of these kind of diagrams, that the standard deviation bars that you will find over here are much tighter. And they're simply much tighter because you're stable. Right? Over here, you're not stable at all. Your fit is not, your fit is changing just by one data point change, your fit change. That's bad. If you ever come up with a fit and it completely goes kaput when you add an additional data point, you might as well go consult an astrologer. Right? There's no point in any of this stuff. Overfitting is astrology, basically. Okay. Okay, we'll finish. Should I stop here? Actually, let me battle through this part and then we'll get a nice break. Okay, so I've been alluding to this notion that even though you have overfitting happening at this extremely high, fit to 20th order polynomials, that there is something we can do called regularization, which allows us to be kind of loosey-goosey and say, oh, I'll fit a 20th order polynomial and I'll do something else. This something else I'm talking about is what's called regularization, or it's putting a complexity on penalty. Putting a complexity penalty. And the idea is, if we go back to this graph, is that if I actually chose, for example, like a $13 polynomial instead of a $3 polynomial, I'm too complex. So I'm somewhere over here. But the idea is that if I somehow constrain these 13th order polynomials by saying that the coefficients can only take certain values, I might be able to do a better job. Okay? So it's saying that it's not the entire set of polynomials, it's some subset of the polynomials. And I can do a better job. But if I actually try and constrain it too much, if I do too much of a good job as far as this is concerned, I may constrain it too much, and then I go into this underfit mode. So you want to do some constraining, but you don't want to do too much constraining. It's a different notion of this complexity idea, right? There what I was saying is I'm going to float the order of the polynomial. I'll let you do lines, quadratics, cubics, multiple order fits. With the complexity penalty, what I'm saying is that it's all 13th order polynomials. I'm just going to not allow you to choose all 13 order polynomials. I'm going to constrain the 13 order polynomials to some degree. So this is kind of like have your cake and eat it too, if you do this constraining part well. And so what's the game we play to do this? Let's go back to our friend, that sine curve that we had earlier. Okay? So what's happened over here? In the diagram on the left, you can see that I have a few points which I've picked. I think in this particular case, I actually picked 3 points or something from the sine curve, and I fitted a line from these 3 points. Okay, and so depending on where those 3 points were chosen, I'm going to have these lines all over the place, right? I mean, the worst line would be the one that comes from here to here. That would be completely flat, and from here to here would be completely up. I mean, I can't get any line whatsoever I want, but I'll get a good set of. Now, on the right side, what I do over here is I constrain the sum of the squares of the intercepts and the slope. So I have intercept square plus slope square. Okay? I say that intercept square plus slope square must be less than a certain number. And that number is what I call this number alpha, and over there I put it as 0.2. So what's going to happen when I do this? Let's say I don't constrain the intercept at all for a second. I only constrain the slope. It means that my slope is going to be between 0 and 0 and plus or minus square root of 0.2, right? Because that's all it can go. So what's happening in this case? What kind of lines have I eliminated from this?
I think all the outliers that you won't reach all the outlier points.
No, what kind of lines have I eliminated?
Slope greater than square root of 0.2.
You're right, so very steep lines, right? I've eliminated very steep lines, so those steep lines are gone. And the sine curve is not a steep thing. So I've eliminated all the steep lines. Same thing with the intercept, right? Now assume that I fix the slope to be something. Let's say I fix the slope to be 0 for the sake of argument. And now I can float the intercept between square root of 0.2 and minus 0.2. But now I'm constrained that the intercepts between those two things. So the intercept is just going to go, for the lines is going to go in a very, very small thing around 0. In a very, very small, well, here it's a little bit different than 0, of course. But the intercepts are very much constrained to be in a particular region. So that makes sure that I don't get something up there and down there in my fit, essentially. So this is the basic idea behind regularization. That's that, okay, I'm actually going to constrain, here's the space of all possible two-dimensional lines, but I'm only going to allow you a subset. And the subset I'm going to allow you is the subset where I square the intercept, I square the coefficient, the slope, I add them together and make them less than something. So that's the game I play. And it turns out that you can actually show that it's an equivalent of minimizing that distance, basically. And that distance is basically what you had earlier, which was a square distance, plus a number alpha times the squares of the coefficients. You can intuitively sort of see this, right? Well, what it's basically trying to say is that for a given value of alpha, don't let the theta squares get too large, because it's just going to add to my risk. It's going to add to my cost. It's going to add to my loss. Don't let it get too large. Now, the way as alpha changes, this thing changes too. If alpha is equal to 0, I get back the old problem, right? Which is that I'm not actually constraining anything by doing this. As alpha becomes larger, the constraint turns up more and more and more and more. As alpha becomes extremely large, my first term won't matter at all, right? Because the second term will actually dominate everything. And when I do that, well, I'll send all of my coefficients to 0 because I want to minimize this thing. So the way to minimize it is send all the thetas to 0, and I won't have any fit left anymore. And you can actually see this over here. So these are 30th order polynomial fits on the left side. In this one over here, I've set alpha to be 1, which is a fairly large value of alpha. See what happens. I just have the first few coefficients non-zero, and the rest of them were all set to 0 by this minimization process. And so you can see that what happens is this is the curve I'm trying to fit. This is the curve I came up to. This is like my 4th order polynomial curve that does this. Not expressive enough. Bias region. Okay. This one is alpha is equal to what are these? What's the value of this? 0.001. At 0.001, I have some of these coefficients non-zero, some zero, and quite a few of them zero, and some of them non-zero. There may be 7 or 8 of them non-zero. And I actually do a fairly good job in the main part of this curve in capturing. When I set alpha to be extremely low, that's 10 to the minus 5 over there, and I now try and fit it, basically. I'm still not doing a terribly bad job. I have really low values in the coefficients out there, but it's a worse job than the one you see over here. And the case up there is when I set alpha is equal to 0, so I actually get back my old problem. I am trying to fit a 38 order polynomial to this data, and it's doing all this dancing all over the place. So you can see what happens is as I turn on this alpha spigot from 0 to some value, basically, it stops the dancing because it gives me subsets. As I turn it too high, it basically freezes. What happened? It basically freezes everybody in place, and
Someone's playing.
it's actually not bad. Maybe you can
the big light?
No, this is good. No, that doesn't help you see this plot though. I should use a better color next time. Well, I'll share these so you can see this. Right. So as you increase alpha coefficients, and it's not the only way you could do this. Remember when I said we talked about distances, you could actually use the absolute value of the distance instead. So you can use an absolute value of the coefficients too. And this kind of thing is called, so the above thing where you actually square the coefficients is what's called ridge regression. And the thing where you actually put in the absolute value is what's called lasso, it's what's called lasso regression. And lasso regression has a very interesting property that it actually sets a whole bunch of these alphas to exactly 0, basically. And so it's a very interesting thing because what it does is that it automates feature engineering. You can think of all these different orders of the polynomial, right? Like x squared, x cubed, x fourth has different features in your problem. And what this is doing is sending a whole bunch of these to 0 and saying, I don't need those features. Now, just one second. So in general, when I solve a regression problem, right? So over here, I have a very sort of like cooked up problem because it's easy to understand what's going on in a cooked up problem. One of the standard problems you will actually see on various blogs and all over the place is this famous old Boston housing data set, where you basically have this house prices in Boston against a whole bunch of things like square area, some kind of indicator function for what locality it's in, upkeep of the place and all of these kind of things. And you can write this huge big regression model, which basically tells you, here is the price as a function of all these other things. And then when you do a regularization, it will basically tell you which one of these, if you do a lasso regularization in particular, it will tell you which one of these things is important, which one of these things is not, basically. And so it's a great thing to do a bit of feature engineering. It's used extremely hugely. For even in neural networks, it's actually used to try and figure out, which features are not actually important to understand what's going on. And so that's the final solution over there. I mean, which turns out alpha is equal to 0.01 turns out to be the best fit in this particular scenario. And these are all 30th order polynomials. So here you've got a 30th order polynomial. Instead of saying I'm going to actually constrain the complexity by choosing d, you're setting d to some extremely large number, and you're saying I'm going to actually constrain the complexity by choosing what the coefficients are. It's another way of doing the same problem. And this is called regularization. The idea roughly looks like this, is that what this is doing is if you go and look at this formula here, those are squares, right? y minus hj squared. So basically, that's something of the type a0 something square, something times a0 plus something times a1 plus something times a2 plus something times a3 squared. The general notion of what that looks like is an ellipse, basically. Okay? And then this next one is basically a circle in 2 dimensions. In multiple dimensions, it's an ellipsoid of nth dimensionality. In 3 dimensions, it's a 3 ellipsoid. In 4 dimensions, it's a 4th ellipsoid. And this becomes a sphere in 3 dimensions, and a 4 sphere and a 5 sphere, which I can't visualize it, but you can get an idea of what basically. So what you're doing, and this is a 2-dimensional thing to kind of look at it, is that, and delta out here is the alpha I was using, that where basically, these are the ellipses of the first term in the distance. These are the ellipses of the second term in the distance. When I had that alpha to be 0, and here he's calling it delta squared, I was over there. When I turned that alpha spigot on, I came down here. And if I turn out to make this alpha almost infinite, basically, by infinite I mean extremely large, then that term has no value and my solution looks like this. And the best solution, the one that actually minimizes the sum of these two and has the right complexity is somewhere in between those two, where these contours meet. And so that's what's actually happening.
But for Lasso, it would be a diamond, right?
For Lasso, it's a diamond. Yeah, exactly. For Lasso, it's a diamond. Which also explains why some things get set to 0. Because diamonds have these sharp edges, and it's quite easy to clip them. It's not that easy to clip it along the tangent line, but it's easy to clip an edge. And once the moment you clip an edge, you basically clip a 0. I say, boom, you're out, basically. Okay, so I'm going to stop here. Yes, there's a question.
If you perform Lasso on a polynomial equation, so if it sets some betas to 0, then we are not following the hierarchical structure of any model. So for example, if we fit a integrated polynomial, so if the beta of x squared is 0,
Yeah.
after performing Lasso, we are not performing the hierarchical structure of
No, we're not. But well, we might actually be kind of lucky having figured out that there was actually no x squared term in this data. You see, this is the point, that what we were doing earlier was actually somewhat restrictive, right? We were saying that I do want an x squared term, I do want an x cubed term, I do want an x4 term, but maybe I stop it there. What Lasso allows you to do, or even Ridge for that matter, if it actually sends the coefficient to an extremely low value, is that basically it's saying, hey, there may not be an x squared, in this example here, it's basically saying that isn't. So that's sort of like 1, 2, 3, there isn't a 4th order polynomial term in this thing. Then there isn't a 5th, 6th, 7th, there isn't an 8th, 9th, 10th, and so on and so forth. But there is a break. And maybe I didn't need that 4th order. So this is actually kind of cool because it tells me that normally if I had done this, I would have said maybe I'll take a 6th or 7th order polynomial to fit this, and I would have had some coefficient for that. This is why I don't need it. So then I don't have it. Parsimonious model is always good. Basically, it doesn't matter how you come up with a parsimony. Basically, there's this thing called Occam's razor, and the basic notion of Occam's razor is don't make things more complex than they need to be. Basically, because something will go wrong, you will overfit at some point if you don't do that. And so this is what it's doing. It's saying, okay, I don't even need 4. Out. Yes?
aren't you trying to artificially lower the weight of the coefficient, saying this is not as important as something else?
Yes, that's exactly what it is. It's basically saying that here is this multidimensional space in which these things live, right? There's like this kind of multidimensional space. Imagine this space in 100 dimensions. It's basically saying so I think what you're arriving at is actually a fairly important point in all of this. All of machine learning is basically this notion that your problem, you think, lives in some really complicated high-dimensional space. Like in this case with the 30th order polynomials, it's a 30-dimensional space. And like, this is a really complex 30-dimensional model. Even a neural network is this really complex thing with all of these layers, and so on and so all of these different neurons. But what neural networks learn for you, and what this thing sort of like, gets for you, is that no, it's actually not living in a 30-dimensional space, but there is some, in this particular case, let's see, 1, 2, 3, 4, 5, 6. There is some specific 6-dimensional subspace of this 30-dimensional space. And it might look really weird, right? It might be some kind of weird, curvy manifold in this 30-dimensional space where the problem lives on. So it's basically saying that the problem is actually a lower dimensional problem than you think. And this is another way to think of machine learning. Machine learning is basically this notion of finding the correct manifold, the correct kind of geometry that your problem lives on. And if you found the correct geometry, then your generalization becomes easier because things will fall in this geometry. It's almost like, you have a sheet and you're waving the sheet in 3-dimensional space and something lives on the sheet. The sheet may be undulating in some fashion or the other. And your job is to figure out those undulations of what it is. But the problem lives on the sheet. The moment you've got that sheet, any point on that sheet, I can now plug into the formula and I can get an answer out of it. So yeah, it is finding a lower dimensional representation of things.
It is just enough for prediction, like other ranges.
Pardon me?
It is good enough for prediction, predicting other ranges outside the.
Aha, so therein lies this big question, right? So that actually violates that first notion, right? Is it representative? Is your sample representative of the population? And the answer is maybe it's not representative of the population. So there are ways to deal with this, but you have to do some kind of mapping, some transformations. And they go under the aegis of something called transfer learning, for example. And it's used a lot in neural networks. Because training neural networks takes so much time, even with all the new technology we have. So ImageNet is a very good example. ImageNet is this huge data set that people do all these benchmarks on. And it's a bunch of images. So people will train on these on ImageNet, then they will actually save the model. And you might actually find that your commercial camera uses a model which has been trained on ImageNet. Now it's trying to do it on your picture. So it has to obviously do some transformations to map it into the domain of interest. But yeah. But so what you're trying to do is, in general, if you're training on something, you're trying to find as representative data set as possible. Okay, so let's take we've been going for about an hour and a half. So let's take about a 10-minute break, 15-minute break, and come back and then go for until the end, I suppose? Yeah. So let's say 15 minutes. So let's see everybody here at 10:25. No, wait, is that? Yeah, 10:25. 11:25, yeah. Shut the recording off. Yeah, just 1 second. Pause recording. So to those of you who have been, who are perhaps like me and have a tendency to think of things from a statistical perspective, you might be a little bit uncomfortable with all this minimization of rest, because it seems very ad hoc, in a sense that what I'm doing is basically I'm going to, in general, to solve any one of these problems, I'm going to create some sort of distance function, some sort of risk function. I'm going to minimize this risk function, and I'm going to be done with it. That's the game that I'm going to be playing. And it turns out that at least for some of these models, it's not true for all. It's a perfectly reasonable way to do things, this kind of heuristic minimization. But for at least some of these problems, that is actually a probabilistic interpretation for it. But it's very useful to think about the probabilistic interpretation because it leads you to more models and more ways of thinking about this problem. So one way you can think about this is this notion of trying to model that stochasticity that we found. Remember we said that, I don't know, sometimes we're talking about voting Republican versus how religious you are, and I don't know anything else about you. I don't know whether you're black, you're white, whether you're, a low-income person, a high-income person, all these other features about you, I have no clue. So these become noise for me. But so I can then sort of make the point, I say, okay, this is all noise, and let's assume that because of all these various features, that if I had multiple people, right, all of whom were just identical in their religiousness, but different in all of these things, and these multiple people would, their chance of voting for Romney would fall on some kind of distribution. And let's say for the sake of argument, because a lot of things in the universe tend to be Gaussian distributions, so this is a Gaussian distribution. And the Gaussian distribution is basically this notion of a bell curve. Okay? Now, if I had 3 data points, okay, at 0.5, 1, and 1.5, which of these 2 Gaussians is this data more likely to have come from? The one on the left or the one on the right? On the left, right? Because what's happening is that the peak of this distribution, which is the place the probability is highest, essentially, is aligning itself with the data more. So this intuitive notion is what's called likelihood of the data. So what is the likelihood of the data? It's higher under the model on the left, which is a Gaussian with its peak at 1, as opposed to a Gaussian with its peak at 2.5, where those data points come up in the tails, basically. So in other words, you would say that the Gaussian on the left is more likely. And so then the game sort of like becomes, let's actually find which is the correct Gaussian? The Gaussian is parameterized by two things. It's parameterized by how wide it is, right? If it is really not that wide, it's going to be extremely narrow. And it's parameterized by where it is, right? Is it at 1? Is it at 2.5? Is it at 100? Where is it? So it's these two things. So I could instead cast this into a problem of trying to find a probability distribution which looks like this data. So this is the basic idea behind a technique whose name you'll probably hear in different talks around here and elsewhere, called maximum likelihood. So you're basically trying to maximize likelihood. And the idea there is that you assume that these three probabilities on those 3 points at 0.5, 1 and 1.5 are independent of each other. Because they're three independent measurements. They're three different people who have nothing to do with each other, essentially. So these measurements are independent. And you multiply the probability under a particular model. So under the model with either theta is equal to 1 or theta is equal to 2.5 here. It's two separate models. So under that model, you find the probabilities, you multiply because these are independent things. So it's like P1 times P2 times P3. And then it's another P1 times P2 times P3 for theta is equal to 2.5. A third P1 times P2 times P3 for theta is equal to 5. A fourth one for, you get my point, right? There's going to be lots of P1 times P2 times P3s. And what you're going to do is you're going to find the maximum P1 times P2 times P3. And that's going to give you the model. This is a completely different approach of doing this thing. And it's called maximum likelihood, and it's the way statisticians have been doing this for years. And kind of schematically looks like this, basically. So if you're trying to do a regression, basically you're trying to say what y is most likely. So I'm going to do a Gaussian distribution along the y-axis, and I'm going to take those various points over there. So you're maximizing this quantity over there, where the symbol pi, this kind of big pi symbol, is basically a symbol that says multiply. If you see a big symbol that says sigma, that basically says sum. That's the one down there. So what it's essentially saying that these are independent probabilities, I'm going to multiply them, and then I'm going to find the theta which maximizes this. So remember what I did in the previous thing, is I found the theta, the w, whatever you want to call it, the coefficients, which minimize, basically, the risk. Here I'm finding the theta which maximize the probability. Now, it turns out to be numerically, actually, this is kind of funny, because it turns out to be numerically easier to do if you actually maximize the log of that quantity. And it's a perfectly reasonable thing to do, because a log is what's called a completely monotonic function. If something is strictly increasing, the log doesn't change that behavior. So it's kind of a very safe function to minimize instead. So you minimize the log instead, and logs have this very nice ability. What they do is that if something is multiplied, log of a times b becomes log a plus log b. So things become additive. So that formula then becomes an equivalent minimization, that should actually be here on time down there, of that quantity below.
Shouldn't that be minus 6?
Equivalently, no, I'm still maximizing. I know.
Is it like probability of less than 1 log? I mean, is that P of x I over lambda? Is that between 0 and 1?
Yes.
So the log would be negative.
Yeah, that's fine, but you're still maximizing the sum of those logs. That's okay. Yeah, I mean, I see what you're saying, that it's going to be a negative quantity, but it's going to be a less negative quantity. So you can, if you want, put a minus sign in front of it, right, basically, and then you're going to minimize those. And that's actually, so I'm giving away the story. If you put a minus sign in front of it and minimize, it turns out, in any specific case, it actually turns out to be minimizing exactly the risk that you had before. There was a question? Yes?
We have the probability of xi given some theta, and if you have sort of a continuous Gaussian distribution, is the probability of any given observed value 0? There's no area.
Could you repeat that? I'm not sure.
Where are you getting the probability of xi?
It's a density function. It's got a probability.
Yeah, no, so you're saying, yeah, it's the probability distribution function.
Okay.
Yeah, it's a function which is basically saying what's the so if I had a value of theta,
yeah,
right,
mm-hmm.
I have a distribution.
Right.
Then the question is, for a given value of x,
yep.
what's the probability? That's one number.
And that's just a high detector.
That's the height of that curve. And then I'm taking that one number and I'm multiplying it over all the data points I have. And that's going to give me a number. Now, for the same theta, for another theta, I'll do the same process. And I'll do this for multiple thetas and see for which theta that product is maximized. Okay, so equality I can maximize the log. And going back to this notion that I said earlier of samples and populations, right? I mean, so you've got one particular sample, right? Where is this distribution coming from over here? Why is there a distribution over here? I seem to have only one set of samples. I should have a distribution. But remember that's the pretense we're always doing when we're talking about statistics. We're pretending that we actually have a million different samples. So a million different possibilities of data over here. And each one of those data points is going to give us a different line to fit. That was all the hairy stuff we were showing earlier, basically. And so exactly what's happening out here is that you can think about each of this particular points as a draw from each one of these Gaussians. Here's a Gaussian, it's a probability distribution. I'm getting a sample from it. I throw a dice loader to the Gaussian distribution. And it says, okay, that's your sample. Well, that has that value of y. It's giving me values of y. I do that for each one of my x's. I get one data set. I do this again. I get another data set. This is how I'm generating my data set. It just happens that my actual data set, I'm assuming is one of these data sets, basically. So I'm assuming that those data points in my actual data set were generated from a process in which there was a Gaussian distribution for each one of these points. So that's the kind of game we're trying to play. And this is the equivalent picture to the hair picture we saw earlier, basically. Each one of those things in the hair was a draw from this Gaussian distribution. It's actually identically equivalent from these. And the reason it's identically equivalent, of course, is that Gaussians have a very nice property that they look something like, I think I wrote this down way earlier.
21. There's a typo that's right.
Pardon me?
It should be sigma squared.
Oh yeah, that should be sigma squared, thank you. If you take the log of this, it basically gives you x minus mu squared. And so that's why the math actually kind of works out that this is actually identically equal. So then actually you arrive at a bit of a problem over here. And the bit of the problem that you actually tend to arrive at is this. How do I actually predict something? At the end of the day, basically you go to your manager, or your manager comes to you and you say, okay, so for a particular value of x, I want a particular value of y. I don't necessarily want a distribution over there. So there is a problem that you have to solve, which is an additional problem that you have to solve. Now, how do I pick a point on this distribution to report as the actual value? So let me back up. There's a little bit of a subtle point over here. You have at each x just one value of y. Point number one. Point number two. You assume that value of y was drawn from a normal distribution. Point number three. Which normal distribution? That normal distribution is done by using this maximum likelihood method, where you take the product of all those probability distributions, one at each x point over there, and finding the theta which maximizes this product. Okay, so point number four. I now have a distribution for each point. Point number five. I want to draw a regression line. Basically, I want to draw this line over there and say these are the values. So use this y is equal to ax plus b to actually calculate something. What do I do? How do I solve this problem? So one simple way of solving this point 5 is by just plugging in the values of the parameters that came from the fit that you got. And that's going to give you some value of y. And then actually it turns out that the value of y it gives you is kind of like mean value of y. It's going to actually give you that value up there, which is the mean over there. But this is not the only way you could do it. And this is actually a misconception that even very, very experienced practitioners of machine learning have. That is not the only value I could possibly choose. This happens to be a Gaussian distribution. So the mean is equal to the median. The median is the value at which there are equal number of stuff to the left and equal amount of stuff to the right. The mean happens to be equal to the median. But you could actually pick the median instead of the mean. So there is a second process that's going on to pick this thing. And that process is implicitly in regression models done by actually picking the mean. And that process is something called decision theory. And decision theory is actually particularly important in machine learning. And it's particularly important to you as a manager because you are going to have to make decisions. And we'll get to that very soon. But how do you actually pick a value in a model to choose? What y do you report? Do you ask your employee to report, or what y as an employee you report to your manager? Actually depends on choosing something called a decision loss, which is actually different from the thing we minimize. So that's a very, very subtle point, and it's a kind of important point. And why is it important? We'll come to that very, very soon. But I just wanted to bring that in over here to sort of make this notion that these are two slightly separate things over here. So I wanted to predict, and this is a simple way, this is the most kind of obvious way you would have done, is you would have said, okay, I fit for these things, and I got some values for these thetas. I'm just going to do theta 0 plus theta 1x, and that's the y. And I think that's actually a perfectly reasonable thing, and what it gives you is this kind of idea of giving you the mean in there. That's the thing, this viewpoint that you're trying to sort of prove. Okay. But just keep this niggling kind of notion of that I said, that this is not the only point you could possibly predict in your heads for later. You should have a small degree of unease until I actually come to it. Okay, so I should make something very clear, and it's probably already clear to you because I did this linear regression with polynomials. That this is not linear. This linearity that I'm talking about is kind of like a more general notion of linearity. It's not what you might think is just a straight line. When I'm fitting for this polynomial, I am still doing linear regression. When I say linear, it means linear in the coefficients. It's linear in the theta 0, theta 1, theta 2, theta 3, theta 4, theta 5. It's not linear in the x. Otherwise, fitting a polynomial would not be linear regression. So you can choose anything. X, x squared, x cubed, x 4 is one choice. In fact, it actually turns out it's a particularly bad choice. Because these x and x squared, for example, are very what I call collinear. They have very strong correlation with each other. What you typically want to use are what I call orthogonal polynomials, like Chebyshev polynomials. These are much better numerically behaved, and they are sort of like, in some sense, perpendicular to each other, in a sense that I will not go into right now. And you can choose any functions for these. You can use, so here are some. So that's a polynomial choice over there. You can use different Gaussians if you like to do this. You can even use sigmoid functions to do this. And the sigmoid functions are actually kind of important because that's what you do when you do regression using neural networks. Such a function is called a set of basis functions. And there can be two types. The polynomials are global. They span over your entire space. Those Gaussians that I've put out there are actually Gaussians with different points in there. So they are actually local to particular positions. So linear is linear in coefficients. That's something to keep in mind. Oh, and by the way, I'm going to actually come up now with this notation over here, which says that this is what I'm going to represent as my linear regression. That's my x1, x2, those are my different data points. Those are my parameters, theta 1, theta 2, up to theta d. And I'm doing this linear regression, that's what that line stands for over there. And I'm going to get an estimator from that, which is y hat, basically. In statistics, you usually put hats on things to mean the estimators. Yes?
So when you say linear, like it's like the order of the equation is one basically, right? It's not
it's one in the coefficients.
Right.
You're not doing something like a times x plus a0 times x plus a0 times x squared plus, some kind of bizarre combination of things.
Or a0x plus c.
It's linear in the m and the c, not in the x. So it's not what we were originally calling a line. It's not the h1. It's not the linearity which goes into h1.
Oh, okay.
Yeah, this is subtle. It's a linear. It's in the coefficient. So when you hear the word linear regression, actually when I first heard the word linear regression, all I ever thought was that I was fitting straight lines to things, and I was completely wrong. It is not the case. It's like you can fit anything. It's this process of fitting where the coefficients are not at any power that makes it a linear regression. And so when you do like in R, you do LM or something of that sort. Basically, you can fit with any basis you like, any set of functions you like. Okay. And that's what I'm going to sort of like. That's the notation I'm going to use for linear regression because it'll actually come in useful. Okay, so now I'm going to actually switch a little bit and talk about classification. But it's really the same idea that we do. This is the simplest model, and this was done in the 60s, and this is actually the preceptor to neural networks. It's called a linear perceptron. And the idea behind the linear perceptron is really simple. Remember how we actually fit the data with lines? Well, it says we can separate the data with lines too. And the idea is really simple that, if I have W1, where W is this kind of vector over here, and it's basically the slope and intercept vector, but actually reparameterized a little bit. It says W1 x1 plus W2 x2 is equal to some value. That's just another way of writing y is equal to mx plus c. I'm just writing it differently. I'm just saying W times x1, W1 times x1 plus W2 times x2 is equal to some constant. Okay? That's that line. Okay? Let's actually take that constant and let's put it into the regression solver. So we'll actually make it the intercept as part of the thing. And the value for that, the x value for that will be always 1. So when I'm saying it's mx plus c, I'm really saying it's m times x plus c times 1. And then my w is m comma 1. Sorry, m comma c, and my x is x comma 1. And so this actually defines a straight line. So once I get a straight line, the two sides of the straight line actually are when w dot x is greater than 0, and the other one is when it's less than 0. And so if I can actually come up with an algorithm which predicts whether this is going to be greater than 0 or less than 0, I can separate things out on both sides of this line. So if I have data, which is like that, and I draw a line, that line has a particular form, right? Y is equal to mx plus b, which I'll now write as w times w1 times x1 plus w2 times x2 is equal to 0. Then greater than 0 will be one side of it, and less than 0 will be the other side of it. And that's how I'm actually going to do my prediction. So that's the very basic idea behind the perceptron. It's terribly simple, and it's pretty good if the data is actually separable. Once the data becomes not separable, if I actually have a blue thing crossing over into the red thing, and the red thing crossing over to the blue thing, this thing becomes unstable. But this was the start of the whole game. But then people said, remember this probability stuff I just talked about, let's actually put a probabilistic model on top of this. So as an example over here, this is a bunch of data about heights and weights from men and women. I've blacked out which one are men and which one are women for the time being in this. It's just a bunch of data. What I can do is I can write what's called a discriminative classifier. And a discriminative classifier is the idea is it's trying to figure out who's a male given the height and weight of that person. So it's trying to figure out the class C, male or female, given the features X. And here the features are the height and weight. It's modeling this directly. And when you model this directly, basically what you're doing is you're modeling the boundaries between things. You're saying that given the height and weight, so given a point over here, X, where X is height comma weight, is this a male or is this a female? What's the probability? And if I do the contours of the probability, they'll give me something that looks like this. And I'll be able to get a point where it's exactly 0.5. Because intuitively, you would say that if the probability of being male is greater than 0.5, then let's classify that person as a male. If it's less than 0.5, let's classify that person as a female. So that would be the sort of like basic idea that you're trying to do. So this is the notion of a discriminative classifier. How do I do this? So remember the perceptron over there, which is basically saying that I'm on one side or the other side of this w dot x is equal to 0 line. Okay? Well, let me do the following to it. Let me pass that w times x, call it z, and pass it through this function h of z. And what this function looks like is like this. It's what's called a sigmoidal function. And it converts things on an infinite scale from minus infinity to plus infinity. This is going all the way to minus infinity. This is going all the way to plus infinity. And my idea basically is that anything on this side of things will be classified as one type, and anything on the other side will be classified as the other type. It converts these to a probability. And it converts it in such a way that if at z is equal to 0, e to the minus z is 1, and I get 1 divided by 2. So it gives me 0.5. Okay? So anything above is going to be of one type, or male. Anything below is going to be a female, for example. Furthermore, it actually kind of tends to saturate over here, which is kind of useful because that's saying that as you become much greater than 0, so going back to this little thing, as you go way far out on one side of the thing, where you have no doubt that this person is going to be male, the probability doesn't change much. You're kind of saturated. All the action is in the middle of that. All this change is in the middle, basically. So it's got the right shape, basically. So what you do is now you take the output of your linear perceptron, and whether it's greater than 0 or whether it's less than 0, and you put that output, w.x, into this function, and out pops the probability. Okay, so that's the game you play. Why? Because it gets you something between 0 and 1. There's really no better reason than that. There's no deep reason that that's the specific case. That it's just a way of trying to get a probability out of the distance. So basically, if you think about it, this value z is actually telling you how far you are from this change point line, basically. Yes.
Taking a 2 steps back, but like, what's the w dot x? Like, is it like multiplying?
So your w dot x is basically doing a term-wise multiplication. It's just short form for saying w1 times x1 plus w2 times x2.
Okay.
Yeah.
It's like wi xi.
It's a wi. It's summation of wi xi.
Okay.
So whenever I use this dot product kind of notation, it comes from vectors.
Right.
But it's basically just a term-wise summation. It's nothing more to it. It's just a much more compact way of writing it. So this is what's actually happening over here. This is the picture. So this is saying that I have some model, right, which I had to learn to figure out for this line, the thetas, the w's, whatever. And the probability of this model looks something like this sigmoidal function. This is in 2 dimensions. There's a height on one side, there's a weight on the other side. And I have males on one side and I have females on the other side, and that's the probability of being male and the probability of being female. So this is the game that's being played. So what I did is I took that perceptron, which had a distance from that separation line, and I converted it into this kind of probability diagram. So this is now called logistic regression, basically. So we had linear regression, which was to predict actual values. So we use linear regression now to figure out a line which actually divides stuff. That becomes a perceptron rather than to fit the data itself. And we use a distance from that division line basically to get a probability. So it's, in a sense, it's still a regression because we're fitting for the coefficients, and it's still linear because the coefficients are linear. And it's called logistic because this function is also called a logistic function, the sigmoidal unit. Okay. So at this point you're like, okay, this is very good. And now we're going to have probabilities for these points, like this person who is somewhere there. I have a probability associated with that person of being male or female. 70% chance this person is male, and 30% chance this person is a female. Okay, how do I actually classify this person? Now, you might be like, oh, it's 70% chance that this person is a male, so male. But that's not how you do probability things. I mean, what 70% of if you have a coin, and you flip this coin, and it's not a fair coin, it's a coin which lands up heads 70% of the time, and tails 30% of the time, it may still land up tails when you flip it. It's just with lower probability that it's going to land up tails. But you need to flip it. So you must flip coins. And the distribution to flip coins is what's called a Bernoulli distribution. It looks like this. And it looks like this simply because, let's say 1 is heads and 0 is tails. So when x is heads, you just get p. That's the probability of, here in this case, 0.7. And when you get tails, x is 0, so that first term goes to 1, and that second term then goes to 1 minus p. So you get 30% chance of tails, 70% chance of tails. And now you do this many times, and you probably have heard of the binomial distribution. And that's what happens when you have multiple coin flips. So, but this is what you're doing in this particular scenario. You got the output of this logistic regression. That was this sigmoidal function h. You did the w dot x business. That's your z. You got this h of w dot x, and you do this for each and every point. So each and every point, think about it as a flipping a coin. So for each person, to decide whether this person is a male or a female, I give you a way to get a probability, Now you flip a coin. So now you're going to get a distribution for the entire data set. So you're going to get these, if you like, go back to what we were thinking about earlier, right? As I told you, you just have one sample of people, remember. And we're finding out the religiousness. But what we're doing is we're pretending we have a million different samples of things. It's exactly the same game we're playing here. We have one sample of people, but we're going to think of this sample as being one of the realizers. And suppose there were 100 people I was doing this with. So it's going to be one of these 100 coins which I tossed. One set of 100 coins which I tossed gave me the sample that was my data. In general, the process is that if I actually have this population and these probabilities were the right probabilities in this population, when I do another set of 100 coin tosses, I would get slightly different answers. Another set of 100 coin tosses, I would get slightly different answers. Another 100 coin tosses, I would get slightly different answers. Hopefully these answers are stable. If these answers are completely different each time, forget about it, right? There's no prediction. That's what was happening when we were overfit. This is the equivalent thing in classification when you overfit is that this is what happens. That essentially every time you do these coin flips, there's a different set of coin flips, you get a completely different set of, and then you're again host. You can't do anything. This is a bad model. You overfit, basically. So again, so this is it's really important, therefore, to sort of understand this basic notion of statistics, in which actually you just got one sample, but you're pretending you had a million samples, and you're hoping things are stable between these million samples. And the pretense to get these million samples is to actually understand what the inference is, how the errors are in this entire situation, right? So I've got these probabilities. I'll make some answer based on these probabilities, but what you need to remember, basically, is that you actually have a distribution. And it is from this distribution that your sample was drawn. It was a draw for this distribution. Yes?
So basically, like, I'm just thinking aloud, but like, let's say we solve a business problem, like, for our own industry or for our clients. Like, mostly you have the entire sample, like, entire population with you, so you can take a sample and you can say, like, okay, like, this sample is statistically similar to my population, and that's why whatever results I get from the sample
can be
kind of like representative, and then I can rely on the result. But let's say any other models that are open source, like, available to the public, like, based on like surveys or whatever, like, so basically we can't like rely on anything because we don't know what the population is, and there's no way to like say that the sample is very close to the population, right?
Well, so you're making assumptions.
Right.
So I mean, that's part of the secret sauce of being an analyst, right? I mean, otherwise you could have an algorithm do all this. Why not automate your job?
Yeah.
So this is part of part of the reason that we're there as humans, and I mean, we haven't still come up with models which can replace ourselves. We might one of these days. I doubt it's that close by. But I mean, there is a bit of an understanding and a bit of a judgment call that goes into saying, yeah, I don't actually think that survey is that reliable. So any results that come that are sensitive to this, what you would end up doing is a sensitivity analysis to changing the assumptions there, and saying if your results change a lot, forget about it. We can't. This is not actionable stuff. But if our results are not actually that sensitive to changing the assumptions on that particular survey which went into this, then okay, let's go and do stuff. Or let's go and experiment. Let's do stuff. In any case, this is what big companies like Google and all do on their web all the time. You and I don't see the same page because they're perpetually running an experiment on us to see whether we like this or whether we don't like this. Do they know how you and I are different? No, they don't. And at the end of the day, they don't care how you and I are different. I mean, on the bulk, if some of you and I make them money, that's the end of the story, right? In a sense, all online models are sort of like spammy to some degree or the other, right? Because they're like, if there's enough money to be made in 0.1% of the people. So if that's what you need to do, then perfectly fine. So all of these things are kind of like sort of like business analysis that you have to put in. This thing doesn't come out of a model. The model can't replace the human, as far as this is concerned.
Wouldn't that be when you're looking at your data and bias,
if data snooping is when you're actually looking at your test data. You completely hide your test data out. But there's nothing that says that you shouldn't, try and figure out by doing visualization, by doing exploratory visualization, what's the structure of your data. In fact, that will actually help you come up with better models, basically. So data snooping is a particularly insidious thing to worry about, and it's very insidious, specifically when you when you start actually looking at test data. In fact, that's why I would suggest that you don't. I mean, you know what Kaggle does, for example, is that they actually completely hide the test data from you. Now, there's actually an insidious form of data snooping that's actually happening with Kaggle competitions as yet, because you get so many leaderboard results. That's a flaw there. You get some leakage because you get so many leaderboard results from there. But we can go into that in more detail later as to how that happens. So you have to be really careful. And there's also more problems in this, what I call sort of a multiple hypothesis problem. If you try and solve a problem in one way and you fail, and you use another classifier and it fails, and you use another classifier and it fails, and you use another classifier and it fails, and then you succeed and you say, oh, I came up with this nice classifier and it succeeds, and let's use this. You have to ask the question, did this just happen randomly that this classifier worked and the others didn't? And what happens is that the more times you try this, you actually need to make the stringency a little bit higher, and that's what's called a multiple comparisons problem. You can Google it, and you'll actually get the whole idea of how this thing works, basically. Okay, so just backing up a quick second. So what you now do to solve this logistic problem is we came up with these probabilities, but we can recast this problem into a risk in exactly the same way we talked about earlier. We take the minus of the log. So this is where the minus sign you're talking about comes in. You take the minus of the log of the likelihood. And the likelihood that we're writing down now is this likelihood here. It's this Bernoulli. It's a product of these Bernoullis. I'm assuming that each person is independent, and I've got a coin for each person. I'm going to write a Bernoulli distribution for each coin. That's going to give you the probability for that person. I'm going to multiply these probabilities, right? Assuming all these people are independent. And I'm going to take that's my likelihood. And I'm going to take the log of that likelihood, and I'm going to take the minus of the log of the likelihood, and that becomes the risk. And it looks something like this. Now it turns out it's not easy to prove it right off the bat. It's not intuitive like it's in the case of the linear regression where you can see it's an ellipse. That this is actually convex. And so you can use that kind of gradient descent thing to minimize. It is convex, but it's not analytic. With linear regression, the beautiful thing is you actually don't need to do any gradient descent. You can write out a linear algebra formula to do it. And basically, the big problem then becomes to make sure that your inversion of a matrix is stable. Over here, the big problem is that this is actually not analytic. You actually need to do gradient descent to solve this. The good thing about it is that you will find the bottom of the bowl because there's just one bottom with logistic regression. Okay, so that's the game you play. So now this is called a logistic risk. And so the game that you keep playing with these different probability distributions and different models is you have different risks. And that's really the game. And how you structure things changes what these risks tend to be. Okay, so we'll write it like this. Oh, here. Again, it's the same x's and thetas, and you do linear regression on the x's and thetas. You squeeze it through that logistic or sigmoidal function, and you get a value out of it. That's the logistic regression at the top. You can also write it in a slightly different format, which is called a softmax. And the idea of the softmax is actually, you remember in the logistic case, you're saying either something is 1 or 0. It's exactly the same thing there. The value is either 0 or 1, but you write it as separate probabilities. So you over-parameterize the problem over here. So the details are not important, but this kind of formalism is important when you go up to neural networks. Because this lets you generalize to n different comparisons and things like that. So there are two possible choices. The constraint, of course, is that these must add to 1. So it's kind of over-constrained problem over here. It's a little bit more complicated than the logistic regression simply because you're writing it in this particular format, but it's not anything different. But I just want to mention that because the softmax is what you'll do if you ever do a neural network stuff. So in gradient descent, what you're doing is basically you have that bowl and you're trying to go down the bowl. Now, there is something else called stochastic gradient descent. And the stochastic gradient descent is really actually more useful for cases where, where you actually don't even necessarily have something convex. Remember I talked about the kicking business that we have to do? So kicking is basically this kind of notion that I have a system, I have this marble inside this bowl. If I kicked it a little bit, it's stochastic. It moves around. I don't know its position. So it could move in a different place. It's even useful to solve logistic regression problems if your problem is very huge, if you have a big data problem. Because imagine what you're doing. Go back to this formula. Look at this formula. And you'll see that I'm doing this product or this sum over each and every data point in my data set. Now imagine I have 5 petabytes of that. And I have to do that each time in gradient descent, right? Because I am coming down, 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 down. So I'm doing a 5 petabyte problem each time. So what stochastic gradient descent says that don't solve a 5 petabyte problem. Just do a 1 point at a time. Which may not be so good because 1 point at a time will take you off in a completely different direction. So what you do is something called mini batch. You don't do 5 petabytes at a point to 10 megabytes at a point. 10 megabytes of samples at a point. And so you do this sum over like some finite but rather smaller set. And when you do this thing, over time what happens, so what you were doing originally is the gradient descent done over time was you do all the samples at one go. Instead now what you do for stochastic gradient descent is that at each epoch, at each time, you only do one set of the samples. Which set of the samples do you choose? You do some randomization to figure that out. I'm not going to go into the details of that. You can look it up on Wikipedia. Actually has a fairly good article on it. But the whole idea is that I can cut down the amount I have to do, but I pay, and what I pay is that I don't go right down the bowl. Because I only have half of the data. I don't know what the bowl looks like. Remember, the shape of the bowl is given to me by all the data. But now I'm only choosing some fraction of the data. So I may actually have a bowl which looks like this, whereas the actual bowl is like that. So based on the fact that the bowl looks like this, I'm going to move. And that movement may take me sideways, somewhere else. And then I have to backtrack back. So it does this thing. It goes back and forth and back and forth and back and forth. But it has given me this advantage that I can actually do a lot of this stuff in parallel because this data is different. So it actually ends up becoming a little bit faster, even though it seems to be a little bit more like a drunkard, moving all over the place. So that's one of the big things that came, just one second, that's one of the big things which came with neural networks. Even though it's not actually a completely flat bowl, it's this kind of undulating bowl, basically. Because I have a drunk moving around it, the drunk gets out of the minimums, basically. And I go off to different places, and I try different things, and I can do this all in parallel. And that's why we could do it in the 80s, and we can do it now. Yes?
So you choose at each point, you decide at each point, this is a local or a global maximum?
No, you don't know.
So how do you keep kicking, or how do
You basically keep kicking, and what may happen is that you may keep coming back to the same point. Or, if you feel that when kicking, your values don't change too much, you actually don't care. So this is, for folks who are from like operations research, for example, you're actually trying to come to a proper minimum. One of the beautiful things about machine learning is that you actually don't care that you're exactly at the minimum. In fact, caring that you're exactly at the minimum is bad because you might overfit. Because the exact minimum depends upon the exact data you had. And doing stuff for exact data always means that you might actually be sensitive to perturbations of the data. So you want a little bit of noise, you want a little bit of stochasticity in your choice. So in fact, there is one of the techniques you use with stochastic gradient descent is something called early stopping. So you don't go all the way. You don't go until you find a minimum. You just go until it has not changed, for a certain amount.
So quasi-stable.
Yeah, given that you did some kicking. Because otherwise you might be stuck somewhere else. So in other words, I have a diagram somewhere, which I'll come to it, where, if you're at a very high local minimum, it's up here. A kick should get you out of it. But if you're at more kind of globalish minimum, or even there are lots of local minima which are kind of near the bottom, kicks will just go to get you sideways between one another of the things. So your value shouldn't change so much. And if that happens, stop. You're done. You don't care. You want it to actually be a little bit noisy because otherwise you might overfit again. And actually, it's funny because you can show that this early stopping is actually equivalent to doing a bit of ridge regression on the whole thing. So it actually is equal. Early stopping is a way of regularizing your model, as it turns out. Okay, so that's gradient descent and stochastic gradient descent. And what you're now doing is, this is another way of looking at this, which is also what's called, and you probably hear this word as well, it's called generative classifiers. The particular one over here I'm talking about is linear discriminant analysis. What you're actually doing is you are saying, and I don't know if you can see the elliptical contours in here. You're basically saying, okay, I have training data. In this training data, I know who are the males and who are the females. So, step one, remove all the males. Only fit the females. What model am I using to fit the females? Some probability model. In this case, because it's heights and weights, and I have some kind of notion that heights and weights of humans may be Gaussian, I'll fit a Gaussian to it. Then step two, throw away all the females, get back all the males, fit them. Step three, combine the two. So it's fitting one by one. So, and this is what's called a generative model, and it's called a generative model because there is a story for it. Whenever we hear the word generative model, it means that there's a story on how you generated the data. Basically, you said, okay, with some probability, this person is either a male or a female. Or there's some intrinsic probability, if you like, of being a male. This is the P of male. It's what's called a prior probability. And it really depends upon your data set, or maybe your population. Maybe your population has 55% males and 45% females. Something you need to have some kind of a grasp on. So in your training set, maybe you have 50% males and 50% females, right? And so you say, okay, that's what I have. Or it may be completely skewed. For example, if you're a company that's selling that's selling cell phone service, the number of people who stay with your company are likely much, much larger than the number of people who leave. And in fact, the number of people who leave are the more interesting ones because you don't want them to leave. So you're trying to figure out why they left. So you need to know what these prior combinations are. And that's why generative models are very good. Somewhat actually better than things like logistic regression from this perspective because you can actually model these two groups completely separately rather than just try and figure out the distinction between them and get a story for why they left. What are the features that caused them to leave? Maybe they were just jumpy people. I don't know. What the feature was. But so that's why you do these kind of generative models to do this. And you do this separate thing. So you say, okay, so firstly, let's flip a coin and say, okay, are you likely to be male or female? And this is not the coin we were flipping earlier in logistic regression, where I had said the probability of you being a male or a female was 0.7 to flip a coin. This is a different one which says, intrinsically, am I likely to get a male or female in my data set? If I have 70% males and 30% females, I'm more likely to get a male. Once I got a male, I know the probability distribution. And I can give you a number for what's the height and weight, basically, given that you're a male. Once you have that, you use something called Bayes' rule, which is basically a conditional probability formula to invert this, to ask that given a height and weight, what's the likelihood that you're male or female? And this rule is actually quite simple. I think I have a slide somewhere quite early on. Yeah, over here, that's Bayes' rule up there. And it's basically saying it's P of A given B, P of B, it's P of B given A, P of A. And so you can just invert one thing for the other. And if you have some time at the end, I'll go into this slide in a bit more detail. But so that's this kind of notion of generative classifiers, and I'll point out which ones are generative and which ones are not going forward. So here's an example. Here's a virtual ATM. And this was inspired by this particular blog post on the YHAT blog, which, by the way, is an absolutely fabulous blog if you want to learn about machine learning. This is image classification. You're basically taking images of checks and images of dollars and trying to figure out one from the other. Now, intrinsically, this seems like a really complicated problem because if you think about it, here's an image, and even what I've done in this image is I've reduced them all to the same size. Okay, and the size is 337. The 332 cross 137. 332 in the long direction of the check or the dollar note, and 137 in the short dimension. Times 3 for like red, blue, and green. So 3 channels. So that's actually a very high dimensional problem that I need to solve. It turns out that there's this thing called unsupervised learning. And remember I told you that at the earlier session that many times your problem lives on a lower dimensional manifold. And many times that manifold depends upon what kind of classification you're trying to do. Is this a 1 or a 0? Or what are the values of the y's and so on and so forth. Sometimes it doesn't. There's an intrinsic structure. And when there is an intrinsic structure, there are algorithms to discover that intrinsic. One of these algorithms is something you might have heard of. It's called PCA. And PCA is a very simple idea. It's actually this animation sort of like captures what PCA is. That's the data I have. And visually, you can very clearly visually see that this data seems to have a very high variation in a direction going up to the northeast corner of that graph, basically. And if you look at this rotating line, okay, you'll see that as this line becomes perpendicular to those blue dots, it gets a very, very long set of red lines going out to the points. And as it becomes roughly parallel in this direction to the blue dot, you can see those other red lines become much smaller. So what PCA does is that it actually finds out the directions in your data in a huge 332 times 137 times three-dimensional space. That there's it finds a rotation in which most of the variation is. And by doing this, what I can do is I can effectively reduce this problem actually to it roughly turns out to be about a 50-dimensional problem from a 332 cross 137 cross 3-dimensional problem. And what's more, actually, a good portion of the variation, about 60% of the variation, turns out to be in just the first 2 dimensions. So I could now write a classifier which just works in these 2 dimensions. And that's kind of neat because I can show you what's going on. I could equally well do it in 50, but it's kind of fun to see it in 2 dimensions. That's what those first 2 principal components actually kind of tend to look like. Basically, it looks like one is actually kind of picking out the dark spots, and one is probably picking up something from checks. I don't quite understand the second one, but the first one is kind of more obvious that it's picking up the dark spots as something very intrinsic to being a dollar note. Something that you might have intuitively actually thought ahead of time would be the case.
Also, it never offsets.
Pardon me?
Also, the language never offsets because
It
it doesn't depend on what.
doesn't depend on?
Why?
Yeah, there's no overfitting over here. There is no Y, actually. Yeah, there's no overfitting here. Yeah.
So quick question for you.
Yeah.
You say that you will linear transformation for different equations.
Yes.
Yes,
Yes, so there are various kind of manifold ways, like isomap and so on and so forth, which time will preclude me from going into right now, but we can talk more about later, which have a similar kind of notion that they're actually trying to limit you to a subdimensional manifold of your 332 cross 137 cross 3-dimensional things. So this is not the only way to do it. And the problem, as you allude to in this particular case, is basically it's a linear transformation, which may not work. In fact, you can actually think of very simple models in which it doesn't work, kind of like a Rowley or things like that, in which this transformation will not work. But for some things it does, basically. So that's just as a parenthetical comment over here, which will actually kind of become useful when we talk about neural nets in about 5 minutes. That what's happening over here is this is a kind of unsupervised problem. Without we trying to figure this out. And sometimes, so let me go back very briefly to this problem of the males and females over here. Suppose I didn't tell you that there were any males and females in this problem whatsoever. And I said, go try and figure it out by yourself. So it actually turns out that there's a unsupervised algorithm called Gaussian mixture models, where basically you can try and fit Gaussians to this. Which is actually what linear discriminant analysis is doing. It's fitting to Gaussians to this. But here I'm not telling you that there are any classes amongst these Gaussians whatsoever. Basically, I'm just saying go fit some completely random Gaussians to this thing. And if you fit 2 Gaussians, it actually seems to recover the males and the females because there's some intrinsic structure to this problem over there. But I can also fit 3, maybe males, females, and unicorns. I don't know in this thing. So, and there is no intrinsic way to figure out which one is better. But whenever you have a problem which is like this, where unsupervised learning actually does something useful, it should actually make you really happy. Because what it typically means is that if I give you a training set with even the smallest number of samples, like if I told you that this is my data set, no labels, but there are only males and females in here. So you know that there are 2 labels in here, and what's more, I gave you some of these males and females. Out of these like 10,000 data points, I give you like 50. You can actually use that piece of information along with the unsupervised stuff to write an extremely good classifier. And this is what happens a lot with neural networks, basically. And it's what's called you might have heard of the word autoencoders, and that's basically a kind of unsupervised neural network. And those unsupervised neural networks become very useful as pre-training for convolutional neural networks which do images. essentially, because there is some structure in those things, and if that structure can be discovered, like continuity of pixels and so on and so forth, then it becomes extremely useful to be able to do stuff. And this is the analog to that in a much more simple situation of this heights and weights problem, that it actually turns out that you need very few males and females to actually get it because there's so much structure. There are actually two separate ellipses over here.
Do you mind if I do a quick 10-second announcement?
Yeah, go for it.
Okay, sorry for that. Okay, hi guys, sorry for the disruption. So I just have a quick announcement regarding lunch, that we are serving lunch on the first floor. So we are giving away lunch tickets when you want to go down the escalator. So make sure to grab your lunch tickets before you go down. And then we have divided the whole lunch area into 6 different clusters, like database cluster, big data cluster, open data cluster. So if you want, you can choose the cluster of your choice and have the lunch with people that just share the same taste in data science with you.
Classification problem. Who's going to go to which cluster? So the difference between the generative model and the clustering thing is this, that if I know whether you're male or whether you're female, I just model that part of you. I throw a coin saying, a priori, are you likely to be male or female based on my data set? And then what's the probability? That's the formula of the height and weight given the class. If I don't know the labels, the probability distribution that I'm trying to learn out here is just the probability distribution of my heights and weights. I'm just trying to figure out what the heights and weights look like in this whole thing. And then it becomes a sum of these things. And these Z's are what I call hidden classes. And there's an entire class of problems in machine learning, which you might have heard of some of these names, hidden Markov models, Gaussian mixture models, all of these, in which you actually have these hidden classes, you don't know what they are, you don't care what they are, but basically what it does is that it lets you create what's called an embedding, which is a lower dimensional representation of your data, a lower dimensional manifold in which things live. You'll see this concept, you come back again and again and again. How many people here have heard of word2vec? Yeah, so some of you have heard of word2vec, right? Which is this, basically, it's essentially what it is. It takes language and creates a lower dimensional representation of the language, essentially. And you can use that very well for translation. Basically, it takes a lower dimensional representation in English, lower dimensional representation in French, maps the lower dimensional representations to each other, which is a much easier problem to solve, and then gets you back to the more higher dimensional representation. But this is exactly what's happening. You're finding these clusters in that. It's just a more complicated way of doing it. So that's another one of these themes in machine learning, is that the same ideas appear in different fashions in different models. Okay, so here's another model to do classification. So that's actually my first two principal components. And the blues are the checks and the reds are the dollars. And you can see that I can probably even draw a straight line somewhere, which will misclassify just a few of them. So I could use logistic regression, I could use perceptrons. One thing I can actually use is k nearest neighbors. And the idea behind k nearest neighbors is, okay, I'm here. My 5 nearest neighbors are all red. I'm red. I'm here. My 5 nearest neighbors are all blue. I'm blue. Clearly, this depends on what I mean by neighbor. If I do just one neighbor, I'm likely to be unstable because I don't know what my majority is. If I do 1,000 neighbors, I'm likely to be very stable, and I'm going to give you the same answer all the time. And that's going to be the majority answer of the number of whether I have more checks or whether I have more dollar bills over here. Which regime is this? Variance or bias? No, it's bias. Because what I have done is I've said, okay, I'm going to choose so many of these things. So it looks like it might be variance because I'm choosing so many of these things. But what I'm doing over here is that I'm basically creating an average of the entire set. It's so coarse-grained that it has no information, really useful distinguishing information in it. So it's all of one type. Whereas if I just do one neighbor all the time, there's a lot of information and it's godforsakennly different each time. So that's another way of looking at bias and variance. Basically, what bias is doing is that it's over-smoothing everything. It's too big. What variance is doing is that it's under-smoothing everything. It's the same thing in regression as well. If I use a straight line, imagine what I'm doing, right? If I have a curve which goes like this, like the curves we showed, and if I use an average value to represent it, that's over smoothing everything. One way I could think about it is I could actually divide the curve into 5 different parts and use an average value for each part. That would be a little bit better. In fact, those are the ideas behind non-parametric methods, that you do this over small pieces of things. You can use k-nearest neighbors for the same thing, for regressing as well, not just for classifying. You just say, who are my neighbors? What's the value amongst my neighbors? Boom, that's my value. And so then I have a step function, which I basically. So again, it's this notion of bias and variance. Basically, again, this is the unfortunate thing that you can't see the. So okay, this is useless to show you those two ones. But basically, the left diagram kind of gives you the idea that you get undersmoothing basically. If you just choose one at a time, that blue one, that red one will be different, and I'll have islands of red amongst blue. If I oversmooth it, I'll represent even those things that I should have started representing these guys as probably blue, maybe making a cut somewhere like that. But now I start saying that these guys are red as well because I have majority red because I went too big. So this is another kind of model where there's this kind of bias and variance, and you can do exactly the same game. And in this case, thankfully, what you can do is k now is your complexity parameter, right? How many neighbors to choose? It's the equivalent of your d the previous time. So you use cross validation to pick k. By the way, so somebody asked me a question during the break, which I should be a little bit clearer about. How do you pick alpha in the regularization problem? You pick that by cross validation as well. So you just replace one cross validation problem by picking d by another one by picking alpha. But it at least allows you the luxury that you can choose a more complex model to start with, basically. So here's what it looks like, and you can see that there's actually a huge area in this particular problem where the surface is actually roughly the same in terms of its standard deviation width, and it will give you almost equivalent results. Well, so any one of these would be a perfectly reasonable model to choose to solve this problem. Another model is called the SVM, the support vector machine. The support vector machine uses a different loss. This is, by the way, the log loss we use for regression. This red one is the logistic loss. That's what it looks like. The support vector loss is called a hinge loss. It looks like this. And it goes kind of steep on the other side. So this is, imagine that everything out here is male. And this is female. And so if you're trying to find males, you penalize a female by a huge amount. That's the whole idea behind support vector machines. And what that actually ends up doing is that it lands up doing what happens over here. So normally when you use a logistic regression or a perceptron, you're drawing one line in between your data. In a support vector machine, you're trying to draw a band. What's more, you're trying to figure out which is the biggest width band that you would get. So if you look at this particular diagram here, you can see that if I drew a band over here, one over here, that's going to be relatively small because it's going to get, banged up against this and banged up against that. If I draw one over here, it's going to be relatively big because it's going to be able to go all the way. If I use the other one, it might be small as well. So you basically find the line which gives you the biggest band around it. That's called a margin. That's why this is called a max margin classifier. And the whole idea is that what's the band which sidles up to the nearest thing of the other type? The nearest thing of the other type is what's called a support vector. That's why it's called a support vector machine. It's the thing that holds up the bands. And now you're like, okay, you've done this. It's a great idea. So, instead of using a line, I'm buying myself some kind of space by having this band. But what happens if there's stuff crossing over onto the other side of the thing? A, I may not be able to find a band. B, my band is very sensitive. If I move that support vector, even one of the support vectors a little bit, my band might change. What's the word for that? Every time you move just one data point a little bit, things change. Overfitting, right? Exactly. So what you do is you allow, for instance, support vector machines for something called slack vectors. And slack vectors are basically things that go on the outside and they reduce your overfitting. They allow a little bit of slack in the whole problem. So support vectors is basically hinge loss plus a term which allows for these slack vectors and regularizes the problem. So again, it's the same story. You have a loss which is unregularized and you add in the regularization term. The interpretation in support vectors for the regularization term is the slacks. You can use kernels with support vectors. Actually, I think I'll skip that part. Another set of models is decision trees. And decision trees basically split up the space into things along axes. So they're not that flexible from that perspective, but you know, if you have 100 dimensions, it's basically making cuts along that dimension rather than, you know, at some angle to them. But you can arbitrarily cut things up, so you can actually go very fine grained into stuff. Why should that worry you? Overfitting, right? I mean, generally you can answer overfitting to almost any question with a good chance that it'll actually work. So that's decision trees. Then there's naive Bayes. Naive Bayes is kind of a little bit of a bizarre thing. So here's an example. So which basically says that your likelihood of having diabetes is high if you are old, if you're pregnant, if you're heavy, and also if your glucose tests and your insulin tests came out very high. Now, if you're me, you'll think that I have the causality all mixed up. Right? The last three out here should be the causes of diabetes, and the next two should be the resultants out of it. Naive Bayes is a rather weird model which doesn't care. It says I'm going to lump all of these things together, and I'm going to multiply the probability of these things as if they were independent of each other, which they're not. I mean, if you're likely to be heavy, you are likely to probably have glucose issues. Because you're basically not, converting you're converting fats into sugars in a much easier fashion. But it really works well, and one of the reasons it works well, especially in medical fields, is because there are so many different ways data can come in, that with so many different complex ways that these things depend on each other, you might as well assume it's independent, and things actually end up working. It's used in spam filtering a lot as well, and where you think it would not work. I mean, after all, the odds of finding Viagra in an email where the word penis is there is way higher. But the assumption you make in naive Bayes is that this is completely independent, and it works really well. The reason it, of course, works is that what happens is that it basically worsens things in the direction you want it. You're saying that this probability is this much, and the probability is that much. It actually worsens the likelihood this is a spam email, not makes it better, that it's less likely that it's a spam email, and that's exactly what you want in this particular case. So it goes in the correct direction, thankfully. Another bunch of classifiers are basically ensemble classifiers, and they're basically an idea to sort of fight overfitting. So remember we talked about those decision trees, right? Essentially. Here's a decision tree for a data set on Variance, basically. And you can see it comes up with all these small regions, basically, over there on the left, essentially. And if I did my data set slightly different, it would come up with a completely different decision tree. And a slightly different, completely different decision tree. So I do something I call bagging, basically. And the idea behind bagging is simply I will take my data, I'll choose some 60 to 70% of that data, and I'll sample that data with replacement. And then I'll train a decision tree on that. And I'll train another decision tree on that. And I'll train a third decision tree. And then basically I'll do a voting between these decision trees. I'll say, okay, what do you think this is? Okay, this is a wine. This might be a Merlot. What do you think? Merlot. Okay, so there are, out of these 100 classifiers, 55 of them say it's a Merlot, and 40 of them say it's a Cabernet Sauvignon. Okay, so I'm going to choose it's a Merlot. And that's the game you play. And the reason this works is basically what it's doing is that each one of these classifiers is bad. It has a lot of variance in it. It's overfit. But by combining multiple overfit classifiers, it's very likely that they overfit in slightly different ways. So it's basically saying, remember that hairy stuff I showed you in the regression? The same thing works in the regression. If I take all that hair and I average all of those curves out, all the stuff that's really hairy will cancel each other out, and the basic trend will get amplified. So my signal to noise gets amplified. That's the game you play with ensembles. And ensembles are really good. Like, the Netflix prize was won by an ensemble of a huge number of classifiers. Another way to do ensembles is boosting. And boosting basically says, okay, I did a classifier and I got some things wrong. So it was a bad classifier, it got a lot of stuff wrong. Let's put more weight on those and reclassify. That's the basic idea. And it has a very similar kind of structure, which I won't go into either. Another set of classifiers comes from these neural networks. These neural networks are actually really kind of simple ideas. The reason they're working now, and they didn't work back in the 80s and 90s when they were actually first come up with, is that we have lots of data now. We have lots of power. We have GPUs, which are really good. And what we've done is because of this, we have started creating deep networks. So deep networks are the equivalent of choosing a polynomial of order 30 and doing regularization, which we could not do earlier with neural networks. If the neural networks could do all of this, we were actually kind of happy, but we would not be like terribly excited about things. But the reason for the huge amount of excitement is that neural networks seem to be this bizarro combination of complicated models which do this, which can be regularized in some reasonable fashion, but also they give you an idea of what their representations are. So they do this kind of both supervised and unsupervised kind of thing at the same time. This is the data set that everybody, and probably you will, if you ever do this stuff at TensorFlow, work on first. It's a postal data set of zip codes, and it has these different numbers, and you want to predict what a number is given somebody's handwriting of the number. And what you do is you have, each one of these is a 28 pixel cross 28 pixel thing. So you have an input layer which has 784 neurons basically, which is basically 784 data points, pixels saying 1 or 0, black or white, essentially. And then you have a hidden layer. You can do this, you don't actually need a deep one for this. You have a hidden layer, this one has 15 neurons. You have an output layer telling you whether it's a 1 or a black. How do you implement this? Kind of simple. Let me just actually go to an example of this. That's what you do. Basically, you are doing a linear regression first. You're doing the sum, you're doing a theta and W. You're passing it through that sigmoid. Okay? And you're getting some value out of it. And you could either stop it at that and that would just be a logistic regression. Or you could do one more layer, you take the sigmoidal outputs of all of those things and then pass it through another sigmoid. And see what you get for the probabilities at that point. And now you do the same logistic cost we had, right? The cost function I showed you from the Bernoulli, and you calculate it. And now you're at this point, this is like a little bit wacky. This is a little bit bizarre. What did you do? We had a very good explanation for what was going on in logistic regression. That was the probability that came out of it. And now you went and you did some kind of combination of those probabilities themselves in a logistic regression again. Why? Why on earth would you do something weird like that? The answer goes back to what we had talked about a little bit earlier, where we said when we do linear regression, you don't just have to use polynomials, you can use anything. Basically, the game is that you ought to be able to approximate functions, and you can show that neural networks with at least 2 layers can approximate any function. Forget the noise right now for a second, but without noise can approximate any function I give it. And basically the idea isn't that complicated. The idea is like that what happens is that if I give you one of these sigmoid curves, it looks like this, right? Okay? Suppose I took this sigmoid curve which looks like this, and then I took another sigmoid curve and I inverted it. So I did minus of that sigmoid curve. It would kind of look like this. And what I can then do is I can capture something that basically gives you a little bit of a space at a given point. So it would basically capture a little peak. And I can take any curve and split it piecewise into these peaks. You know, it's like this is this. I can just make a histogram under it, so I'll get these peaks. And then I'll capture each peak using these sigmoids. And my problem then becomes how should I combine these different sigmoidal units together to get this arbitrary function. That's it. That's all there is to neural networks, basically. But what they're doing is they're saying that they're universal approximators, that you can use a combination of neural networks to get this thing. Okay? So that's the game we play. So you can use neural networks for regression. Here's an example of a neural network used for regression. I'm doing this kind of logistic regression first, one. I'm doing another one. I'm combining these together. Then I'm getting a sum out of that. And I do linear regression on that. That's it. That's how I predict it. Again, the reason is, so what this is the equivalent of is saying that instead of using polynomials, x squared, x cubed, or some combination of Chebyshev polynomials, which are all like order 20 polynomials I put together, I'm going to use these sigmoidal curves instead. That's really all there is to it. And I'm coming up with these sigmoidal curves from the data using logistic regression. So, neural networks with neurons layers, all of this actually is basically a way of combining things. It's basically a way of writing sums of different functions. And it's the difference is that this is a problem which is very in a very principled way, write out the cost function and actually optimize the cost function. And the beautiful part of the technology, there's this whole thing called backpropagation. And the whole notion of backpropagation is just a way of using graph structures to basically optimize to write this optimization problem out. How many people here have heard of Spark? Quite a few, right? So Spark, the basic idea is that what you're going to do is you're going to write this program in a very constrained kind of fashion. You can't change your data set in Spark. You can only transform a data set from one thing to the other. What that allows you to do is to reason about the graph structure in Spark. And the graph structure is then used by the Spark runtime to distribute the computation to different machines, basically. It's exactly the same thing that's happening in these neural networks. There is a graph structure. That this next layer of the network depends upon the previous layer, in a particular fashion. This guy is the sum of the outputs of this, and he does not care what happened in the previous part. He says, I've got this O11, O12, and I have a U11 and a U12, and I'm going to combine this with this theta. Sorry, I'm going to combine the output 11 and output 12 with theta 5, theta 6, and theta 7, and I'm going to sum this. I know how to deal with the minimization of the cost function for that part, and that's all I care about. And then I do that recursively about the whole thing, and I'm done. And that's what backpropagation is. It's just basically a way of taking a cost function minimization and writing it out as a graph structure, the way you do a computation and write it out as a graph structure in Spark. It's basically a computational graph. And once you have computational graphs, there are all kinds of beautiful computer science algorithms like topological sort, which some of you may have heard of, to rearrange how these graphs are and actually do the calculation in a much simplified fashion. And libraries like TensorFlow, Theano, all of these different libraries you might have heard for, that's exactly what they do for you. They simplify this whole process and they do the calculation under the hood for you. So neural networks is nothing but actually combining stuff, combined with some cool computer science-y technology to actually get things together. And the basic thing is that this is going to work because neural networks can be used as universal approximators. So the basic way, just to illustrate, the basic way this optimization works is that you have some complicated neural network. You look at the neuron J in layer I, and there are some changes happening in that thing. You see, what if I just perturb those values again? I don't care about how those values came to be perturbed. Think about this as a recursive problem. I don't care about how that happened. Somebody else has to figure that part out. But if I perturb those values over there, that one is going to affect that layer there. And that layer is going to affect these other layers like this. And those layers are going to go blah, 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 somewhere into the future and finally affect the cost function in some fashion. So all I need to know is how the value in one layer changed by a change in the weight of this graph from one to the other. So basically I'm changing the regression coefficient from one layer to the other by a little bit, asking how the output value changed. And now I have different paths along which this works, right? I mean, I can go like that. I could perhaps go like that. So I have these multiple, 100 different paths, and I just need to figure out how these changes were on the different paths and add those things together. This is a problem that graph algorithms can solve, and we don't have to bother about it. And that's the big change. That's the big advantage of using these networks to do things. Problem, of course, is that this is not convex, but I talked about this a little bit. That you go to where you can. Either one of those two minima is fine, and that one is not. So as long as you get low enough using this SGD thing, you're in game. And in fact, what's actually useful is this happens because you have very deep networks. It actually turns out that the wider you have a network and you initialize all these things at a different point, you can actually explore different minima very, very, very fast as well. And you're doing this in parallel, so everything becomes kind of fast. Okay, so you have a neural layer like this. What happens is that as you add more and more layers, basically, the basic game is that you are allowing a more complex model. You're combining more and more of these sigmoid functions, okay? And so your bell should begin to go off and say, overfitting. And that's exactly what's happening. You can learn a boundary. You see this light blue boundary is the one where you have very few layers. The squiggly boundary is the one where you have lots of layers. So what happens is that you can actually learn more and more of these complex functions, and you're like, yay, okay, so this is great. I have very high, it's called channel capacity is the word that people use. I have very high capacity in these models. I can fit arbitrary complex functions, but I gotta worry about overfitting. But that's one of the reasons to use deep neural networks is that, what happens is that most machine learning algorithms at a certain point, they don't have that much capacity anymore. They can't actually fit things particularly well. Deep learning can take more and more and more data and get better results from it, basically. And the other reason to use it is this, is that if I can learn hierarchical features. So if this is the image of this person, the features I get at different layers of the neural network actually correspond to different features. So they're like different image things, horizontal stuff, sideways stuff. And then the next layer these combine to form eyebrows and noses and so on and so forth. The next layer these combine to form faces. And so I actually have this kind of understanding of what my lower dimensional manifold on which this data lives actually kind of is. In fact, one way to think about it is in this diagram out here. By the way, so a lot of these diagrams are from Michael Nielsen's excellent neural network book, which is online. Two excellent neural network books are online. Michael Nielsen, which is not very technical, so it's a great place to start. And the second one is by Yoshua Bengio, who's one of the stalwarts in the field. It's a very technical book, but it's I think it's one of the best written books on machine learning for neural networks. So it's worth, if you're willing to wade through some of the technical stuff, it's totally worth reading, and it's freely available online as well. So this is what's basically, so these features are basically saying, is there an eye in the top left? Is there an eye in the top right? Is there a nose in the middle? Is there a mouth in the bottom? Is there hair on top? And that tells you, I got a face, basically. So that's how these layers compose. And these themselves may actually have smaller layers inside. Like, is there an eye in the top left? Is there an eyebrow? Are there eyelashes? So those are the smaller layer features. And one of the reasons that this does not become a complete free-for-all is because what you're doing in these neural networks, in trying to learn any one of these layers over here, is that these weights, so one of these might be an eyebrow thing, the other of these might be a kind of eyelash thing, the third of these might be a pupil thing, and so on and so forth. All these weights are tied to each other. I'm not having a different weight for all of these things. Like there's a weight from here to all of these, and this is constant for all of these. So weight from here to all of these is the same weights for all of these. So you tie weights together, and that's kind of one of the things which actually makes things somewhat manageable. So autoencoders are, I just briefly talked about it. It's just basically like these Gaussian mixture models, where it's completely unsupervised. What I do is I actually start training a network to learn a smaller representation, which is that green thing, and then I tie these weights over here to this and make them the same. I just the transpose weights on the other side. And so this learns how to basically get back exactly the same thing I had. And so it learns me. So basically this is the same hidden model. Like if I had only 3 out there, this is like 3 clusters. And so that's what it's doing over there. And so it's used to learn these kind of representations like word to back and so on and so forth, which are lower dimensional representations in which you can learn things. In which are much easier to do things in, like translation and so on and so forth. But the big daddy of all of these things are these kind of convolutional networks. And the whole idea behind convolution is that there's some kind of kernel, like you see this thing over here. It's W, X, Y, and Z. And I'll take it first on the upper left. So it's AW plus BX plus CY plus, AB, and F, sorry, plus EY plus FC. And that's what I get over here. Then I move it over by 1. So it goes BW plus CX plus FY plus YZ. And I keep moving it over by 1 and doing this. So this allows me to do arbitrary filters like smoothing and so on and so forth on top of an image. And I can use this. Should have been one more here. I'm missing a slide here. Okay, but I can talk about it. So what I do is I can do this and I can repeat this process. So what I do in my sort of like neural networks then is I start with all my pixels, and I put a convolution on them which basically starts kind of averaging stuff in these pixels. And then sometimes I'll drop some of these pixels and so on and so on. And then I'll again get the representation out of there and I'll do some more averaging. And then drop and so on and so forth. And so, for example, if I was doing face recognition, I might do some combination of these kind of things, simply because what they will allow me to do by doing this kind of averaging and so on and so forth is actually enforce certain locality constraints in this problem, which says that, okay, so I have this image, it's of a face. Likelihood is that the colors in the tones and so on and so on, that face are not going to change, but there's going to be an abrupt change in the boundaries of the face to something else. So it's encoding that information in there. Now, the problem with all of these things is that you can have, as I was saying, this is a model with very high capacity, you have to regularize it. So neural networks are typically regularized in exactly the same way. You have that cost function, and you have all those weights, remember, from one layer to the other. What did we do earlier with weights in regression? We just added alpha times square of the absolute value of the weight. We do exactly the same thing here. But take all the weights in the network and put them with an alpha in front of it and optimize that cost function instead. I got basically a ridge regularization. I can do a lasso regularization which will drop out some of these weights. That's kind of equivalent to what you explicitly do. You just randomly choose in every layer some things to drop out from the network. You just cut this thing out from the network, so all of these things are gone. And what that does for you is that basically it learns a slightly different neural network. And then what you do is you average these things. And so you can do an ensemble average of neural networks. Or sometimes you don't even have to do an ensemble average of neural networks, because essentially this dropout procedure will actually do a bit of this averaging from you by learning a slightly different network each time. So there are these various ways you can regularize these neural networks. Okay, so just to summarize about neural networks a little bit, and actually I'm missing this diagram. I'm trying to figure out where it went. I'll come up with it right at the end, just to show you that, as to how these things are kind of adjusted next to each other. The basic idea, so just to back up and summarize, the basic idea in neural networks is I am going to learn a model kind of repeatedly. What we did this kind of logistic regression at one step. Just combine it again and again and again at next step. The reason this works is because I'm having these sigmoidal functions, or for that matter, some other functions like hinge loss type functions or tan hyperbolic functions and so on and so forth. Combining these functions acts as a universal approximator. I can approximate any function I want, any probability function I want for classification, any general function I want for regression. Because I can do that, I can do things like this, or I can do things like this. The more layers I put in, that's the equivalent to adding more terms in the polynomial. Therefore, I must do some regularization of this. And the way I do regularization is by randomly dropping out some of the nodes in the network. That's called dropout. It's been extremely successful. Or by doing L2 regularization, which is the square regularization we showed, or by doing the lasso regularization, which is the absolute value regularization. I need to. It's critical. Regularization is critical in a neural network. Neural networks are not convex, so they may actually find wrong maxima and so on and so forth. So you have to basically deal with that by doing stochastic gradient descent and by kicking it if it actually settles into a wrong maximum. Early stopping is very useful with this because you see that if it's not changing much, it must be at a minimum which is near the bottom. If it's changing much after kicking, it's not at something which is close to the global minimum. Not being at the absolute global minimum or absolutely inside some local minimum is very good. As long as you're close to it, you're fine. That's in fact better because that's equivalent to doing this kind of rich regularization, and you don't have any of these overfitting issues. Learning a neural network takes a lot of time because you have now put in all these layers. And it's a complicated flow process. But we have GPUs which do this very fast. You can do this on parallel machines. SGD is very parallelizable because you can do this to different parts of the optimization in different places. Finally, all of this would be all very nice, but not really useful if this did not work. The hierarchical learning of the representations. And nobody completely understands why this part works as well as it does. But it does exploit the structure which is there in all successful machine learning projects, which is that there is some lower dimensional structure that you can learn. If there is no lower dimensional structure in your project, likelihood is you won't learn stuff. For example, I'm trying to, we have like a new baby which is 3 months old, and based on all the data I've collected, which I have been, you might have expected, trying to predict when she's going to sleep. Complete and utter failure. It's complete and utter failure. I'm basically beginning to think there isn't a lower dimensional manifold on which this baby lives, essentially. But so the problem needs to be amenable to it. And clearly, visually, images are amenable to this. Your eye picks it out. It's a good chance that if your eye is picking out faces in an image, an algorithm is going to be able to do it. Because your eye is picking a lower dimensional structure out of there. And it's using this lower dimensional structure to figure out that you're the same person I saw yesterday or day before, or whatever. So, once that structure is there, then you can do this kind of thing. Okay, so that's neural networks.
So quick question.
Yes.
You mentioned that adding additional layers to add more complex neural networks that could capture more or could develop more locally, right?
Yeah.
There are earlier studies like maybe 10, 15 years ago that they were also adding additional layers but didn't find any additional performance. Why is this stuff?
I don't know off the top of my head. I'll have to go look. I wasn't familiar with this earlier research, so it's probably worth going and looking as to what was different, what's changed. Something must have changed, and I don't know what it is. Yeah. Yeah, so let me answer a question I have no clue about, but it's probably something changed. So we're actually kind of running out of time. We're about 2 minutes left to do this part for evaluation part. So if it's okay with you guys, I'm going to just stick for 10 minutes longer and cover the salient points of this. So I'll leave it to you guys if you want me to do that or not. Is that okay? So the big thing with these classifiers. So one of the things that we've been sort of like talking about right now in this classifying people as males and females is this kind of notion that if you have a greater than 50% chance, I'm going to say you're a male. Less than 50% chance, you're a female. That's not necessarily a useful way of thinking about the problem. That's kind of an intuitive way of thinking about the problem. But the problem is very different in different scenarios. So let me give you the example. And this is actually you can't see it terribly well on the screen out there, but it's an example of a metastasized breast cancer. So if I have a classifier that looks at mammogram, okay, and tells a person who does not have breast cancer that they have breast cancer, is that a disaster? Okay. Now let's go to the reverse question. If you have breast cancer, and I told you don't have breast cancer, and so you don't do anything about it, well, that's probably, if you want to call the other one a disaster, it's sort of a catastrophe, right? This is the Titanic, basically. So, the cost of making a misclassification of a male to a female or a female to a male in that problem is, yeah, who cares, right? Unless you're in North Carolina. But, on the other hand, if you're in the medical field, this is really bad. Not so bad, but I mean, it depends on your perspective. If you're a business manager and you're trying to retain a customer, and I told you that this customer is going to go, and you offered this customer an incentive, maybe you lost a little bit of money because you offered this customer an incentive and the customer stayed. But if I was wrong, the customer would not have gone. But I told you the customer would go. Okay. That's not such a bad situation. On the other hand, if the customer would have gone and I mispredicted that customer as a person who would not go, that's bad. That's a bad machine learning outcome for you, for the company, because you could have offered me a bigger incentive or something to stay and not leave. But you didn't know I was going to leave. So there is this asymmetry, basically. And the way this asymmetry builds in is in something I talked about earlier, which is this notion of decision risk. This decision risk is different from the risk we use to actually learn the probability distribution. The probability distribution of males and females is what it is. The probability distribution of cancers, that this is something that looks like it's cancerous and this is something that doesn't look like it's cancerous. That's the image. The image doesn't have any morality or ethics or anything associated with it. It's like, okay, I think that there is cancer in this image, or I don't think there's cancer in this image. The morality or ethics comes in, if you like, or the business rule comes in extraneously. It's something that you must build into your risk. And what you should actually be doing is when you do your cross-validation process, and you're actually doing stuff on the validation set, you should be using the decision risk instead. And there are multiple ways. So everything that's in this section is basically a way, if you like, of using ROC curves, which is just another way of trying to figure out how to use this cross-validation to basically test on a different risk than the one you actually train on. Because the different risk is what's really critical in your problem. And the one way you parameterize this risk, essentially, is by making a kind of a truth table of some kind, which is what are your true negatives, what are your false positives, your false negatives, and your true positives. So depending on what you call a negative and a positive out here. I mean, so if positive is if positive is cancer, it sounds like a bad way of saying things. But if positive is cancer and negative is no cancer, right? Then a false negative is a bad thing for you, basically. So you want to create something which basically makes false negatives extremely expensive. You penalize false negatives in a really strong fashion. And the way you penalize this stuff is you use the decision risk. And the decision risk basically goes over all possible outcomes. Okay? So this is that for any one given sample. So say this is my mammogram. It goes over the possibility of having cancer and not having cancer. Given my data, what's the probability of having cancer? That's something that comes out of the image. There's a probability that's being spit out by the machine learning algorithm from the image. That's why I did that. You remember we did that logistic loss? The logistic loss was basically to train this P. Right? We trained the P from there. I multiply it by a loss function which says that, okay, you predicted that I have cancer. What if I didn't have it? What are the H's that I didn't have it? Or you predicted, and you sum it over that, and the probability that I didn't have cancer, and you predicted I didn't have it. And so that basically gives me a loss for that action H. Where action meaning this kind of notion that I didn't have it. Or it could be like, or you can specify differently as a don't do it type thing. So now this loss function actually depends upon what your situation is. And you can kind of, if you like, let me see if I have a diagram for this. Nope. Corresponding to this big confusion matrix here, corresponding to this confusion matrix, what I do is I associate a cost for each one of these things. So, if I predicted a person who has cancer as having cancer, that's good. So there's no cost associated, no risk associated with it. So I'll put a 0 in here. If I predicted a person is not having cancer as not having cancer, that's good too. I'll put a 0 there. If I predicted a person having cancer as not having cancer, that is super bad. I'll put a value of 10,000 in here because I don't ever want that to happen. If I predicted a person as having cancer and they don't, well, that's not good because now they have to go in for a biopsy. I'm being invasive on this. But it's not like super bad. Okay, so I might put a value of 1. And so now this is your ethical judgment. Is that a 10,000 to 1? Or is it a 10 to 1? Or what is it? Now, based on that, what's going to happen is that your probability threshold will completely change. So what actually ends up happening is you can actually write this out in a format which is like this. So this is the risk of 1 happening, which is like, say, having cancer. And I can write it like that. And on the assumption that one of those was 0, then it just basically becomes the probability of not having cancer times the loss associated with predicting having cancer when you don't have cancer. And this one is the other way around, right? The loss associated with having cancer when you were predicted not to have. So now it basically, I look at these two risks, right? And I say, choose one if the risk of the first thing is less than the risk of the other thing. That's what I want to do. I always want to minimize risk. And so when I do this kind of minimization of risk thing, what basically is going to happen is that the values of R are going to completely change. So you can do this formula basically, and it basically says that P0 is going to be this ratio R, where R is that ratio of the losses. So it's the loss of the false negative divided by the loss of the false positive. So let's take this example where the false negative is 10 times more expensive than the false positive, right? Then this R is going to be 10. So then you're going to say the probability of 0, which is not of not having cancer, should be less than 10 times the probability of having cancer, which basically is saying that even if the probability of having cancer is 0.1, which in a normal classifier you would never say that something greater than 0.1 ought to be classified as a positive, as a positive classification. But this is such a gut-forcing and important thing that you say that even if the probability of having cancer is greater than 10%, I'm going to flag this person as having cancer, basically, so that they follow up on it. And maybe they don't. That's great. But I want to flag that they have cancer. So this is the risk scenario that you need to deal with. Now, this actually holds in even more mundane cases, as I was telling you earlier. When you do these risks for regression, you train the model using the squared law. So you train the model using maximum likelihood. And what that gives you, I was telling you, was this Gaussian distribution at each point. So at a new point, you have this Gaussian distribution in y. I've got to pick one number, one action, one number from this. That's the number I'm going to give my boss. This is going to be the sales. Which one of these should I choose? Depending on what you choose as your loss function here, in this risk, whether I choose the square or whether I choose the absolute value, I'm going to get a different answer. The square one is actually going to give me a mean. The absolute value is going to give me a median. In this case, it was a Gaussian, it doesn't matter. But if it was not a Gaussian, if it was some other distribution, which is like an exponential distribution, for example, this completely changes. So even your answer you give your boss in a regression problem changes depending upon what you want to do with it. And you have to choose which one is better, a mean, a median, or the most frequent value, and so on and so forth, to decide what you want to do with this. But this decision risk is most kind of like clear in the case of a classification problem. So just to then finalize, one way you can actually do this in a very principled fashion is using this thing called an ROC curve. And the idea behind an ROC curve is that, remember I had all these different samples when I did this height weights classification for the males and females, or if I do a cancer classification, this person has cancer or not. Okay, so let's order it by these probabilities. Okay? Here's a person with a 1% chance, 2% chance, 3% chance, 4% chance, 5% chance, 6% chance, and so on and so forth. I'm going to order it by that. And basically you can see that this order goes from the top over there to the bottom over there. And I'm going to actually plot the true positive rate against the false positive rate over there. And I'm going to try and get into the upper left corner of this curve, because the upper left corner of this curve is actually kind of telling me where I get a point. So I get a point 50. And that's going to be the place where my classifier actually kind of lives. And so in this case, which I think actually is the height weights problem, logistic regression will tell you to go into the upper corner. However, if I have the cancer problem, this is not what I want to do. Or if I have this problem in which I'm trying to not get somebody to leave me, that's not what I'm going to. That's not what I'm going to do. In those ROC curves, I want to be at a very, very different place. And the place I actually want to be at is basically the place where you have this kind of loss. So you look at this loss over there, and you say, for example, if I'm in this cancer problem, false negatives are 10 times more expensive than false positives. So that value R over there is 10. So then what I look for is lines with this kind of slope. So if I had this thing where I have large R, it basically tends to penalize the false negatives over here. So large R basically is stuff with low slope. So if I want to penalize false negatives, I want something that's on the top of that curve. I don't want to actually be in that left corner because that's the halfway point. So I want to be something very close by that. You can see that the probabilities are much lower, 0.05, maybe 0.1 over there, all the way up to there, we're even at like 0.25 or something of that sort. So I will choose a line over there. So to see how to do this, there's a great book. It's by Foster and Fawcett. It's called Data Analysis for Business. It's from O'Reilly. And this actually gives you a very, very detailed idea on how to sort of like pick these points out. So in both these cases of customer churning or cancer, you don't want false negatives, basically. You have a problem where, you have this, you have this. On the other hand, if false positives are you don't want many false positives, you want to be on the lower side of this curve. So this is one way you can pick things up. Even more usefully, you can basically, remember I said that there's a loss associated with the false positives, loss associated with false negatives, and losses associated with true positives and true negatives, zeros. You can put a negative sign on the loss and think of it as a profit, basically. So in the case of the customer churning, you can see what your profits are, and basically you can actually plot profits against the percentage of the things which were classified to be which were classified as positive. So in this case, what's happening over here? It's like 40% of your cases are classified positive. And the way that works is that if I choose, if I take my threshold extremely low, right? If I say it's positive, everything about probability 0.000001, then almost everything will be classified as positive. I'm here. If I say classify only those things as positive whose probability is greater than 0.999, I'm over here. So my 0.5 should come roughly in the middle over here. If I had like 50%, if I had a well-balanced data set. But that's what I'm plotting. So what I do is I basically say I just keep changing the threshold. So over here it's like 0.999. I make it 0.998. I make it 0.997. I make it 0.996. I make it 0.995, and see how many would have been classified positive. Okay. Based on that, I have a matrix which says, and because on my test set I know now which ones were actually positive and which ones were not. I can calculate what's called an expected profit. All I do is I take this loss or profit and I multiply it by the number of false positives. Loss of profit for false negatives multiplied by the number of false negatives. Loss of profit for true positives multiplied by the number of true positives. Loss of profit for true negatives multiplied by the number of true negatives. Divide by the total number of samples I have. So that gives me the average profit I make. That's going to give me a curve which looks something like this, basically. The peak of the curve is clearly what you want to be at. You want to make a majority of a profit. And that tells you how many, what threshold you should use. So this thing may be at a threshold of like 20% out here, which might have corresponded to 0.75. So this thing is basically saying go at 0.75 and choose that as the value at which you should you should decide whether to whether something is positive or not. In fact, this formalism is extremely powerful because it actually allows you to see to say what it would cost you if you had a fixed budget. So if you have a fixed budget in terms of money, right? If you have you have only $100,000 to spend, and the cost, for example, of a false negative of going and contacting a customer is so much money. If I have to spend $5 each time I contact a customer, and I'm telling you that over here that you've got to contact 40% of your customers, you may not have that much money to spend. So you have to then decide what customers to choose. And since this goes down from having 0.999 all the way down to 0.0, the customers out here are the most likely customers to be positive in this scenario, i.e. positive for cancer, or people who are actually going to leave your company, or things like that. So with a very low budget, you want to target something here, even if it doesn't maximize your overall profits. Simply because you don't have that much money to maximize your overall profits. So again, this is where the kind of business analyst needs to come in and think about this a little bit, because there will be at different spots along this, and you can choose different kind of ways of doing things. So let me stop out there. The example over here is that this is a finite budget, 100,000 customers, 40,000 budget, and then $5 per customer, which means I can only target 8,000 customers. Thus, I must target my 8% most likely customers to change, right? And boom, I target that. That's the max profit at 8%. So even though you can see out here classifier 2 is overall better and makes you a greater profit if you had an infinite number of funds, you have a finite number of funds, you would actually use classifier 1. So sometimes what you think is the best classifier isn't even actually the best classifier. And the best classifier actually depends upon what your situation is, how much money you have, and things like that. All right, so let me stop there. This talk will be up on the website of the conference, I think, in a day or two. A lot of this talk is based on notebooks in CS109. So if you want to see this, for example, just go over here. And in the labs, there are notebooks at each one of these places. So for example, since we're talking about this particular scenario where we're comparing models, so you just go in here, and the entire churn thing is actually worked out over here for you. And you can see what to do for a finite amount of money in this particular scenario. So there's a lot of online resources for this. And Foster and Fawcett's book is also actually really good. Yeah, so the basic thing over here then is, just to conclude, you must decide which is the better model. In a normal scenario, this is actually fairly simple, right? You basically see what's giving you the best performance, and you look at the best performance by looking at your misclassifications. If a model is giving me 100 misclassifications out of 1,000, that's a 10% error. If it's giving me 50, that's a 5% error. Go with the model with 5%. If your scenario is different, like you're predicting cancer, or you have this churn situation, you want to figure out which one of those 5% is it messing up. If the 10% model is actually getting less false negatives, it's making less people who had cancer predict that they had no cancer, that's the model you use, not the 5% model. And that's the take home from the end of this. You can do all this great machine learning technology. If you switch off your brain, it's gonna fall flat on your face. And so the most important thing of all the machine learning thing is that at the end of the day, it's actually your brain is the most important to interpret the results of your data. And I guess that's the take home message. Thanks, guys.